You might think that figuring out the biggest thing in the universe would be straightforward. After all, we can measure mountains, weigh elephants, and map oceans with impressive precision. But the cosmos has a way of making simple questions impossibly complex. The more we look outward, the more we discover that our everyday sense of size breaks down completely. What seems enormous at one scale becomes tiny at another, and what we thought was the ultimate example of largeness turns out to be just a stepping stone to something even more immense. Scientists have been surprised again and again by discoveries that shattered their assumptions about cosmic scale. In this video, we'll explore how the universe constantly redefines what it means to be truly large, taking us on a journey that will challenge everything you thought you knew about size itself. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too. Just like you did, thank you. Now, let's get started. The universe holds a peculiar kind of puzzle, one that grows more complex the deeper we examine it. When we ask about the largest thing that exists, we're really asking about the limits of what can be. And those limits, it turns out, depend entirely on how we choose to measure them. Weight matters differently than width. Volume speaks a different language than influence. Each measurement opens a door to a different answer. Our human experience teaches us about size through mountains that pierce clouds, through oceans that stretch beyond horizons. Mount Everest rises nearly 9 kilometers above sea level, a wall of stone that has challenged climbers for generations. The Pacific Ocean spreads across more than 160 million square kilometers, so vast that aircraft spend hours crossing its expanse. These earthly giants defined enormity for our ancestors. They represented the absolute boundaries of what large could mean. But here's where perspective becomes everything. From space, that towering mountain becomes barely visible, a tiny wrinkle on Earth's surface. Less than 0.1% of our planet's diameter, the mighty Pacific shrinks to a thin blue film, clinging to a rocky sphere. What seemed impossible to comprehend suddenly looks almost delicate. This shift in viewpoint reveals something profound about how we understand scale. Large isn't really a fixed property. It's a relationship between observer and observed. Stand next to a tree, and it towers above you. Fly over a forest, and those same trees become a textured carpet. Rise higher still, and the entire forest becomes a green patch on a brown continent. Earth itself measures about 12,700 kilometers across. That distance would take months to walk, assuming you could somehow walk in a straight line through the planet's core. Yet when we compare Earth to our Sun, something remarkable happens. You could line up 109 Earths side by side and still not span the Sun's diameter. Our ordinary neighborhood star suddenly reveals itself as more than 100 times wider than our entire world. This comparison changes everything we thought we knew about size. The Sun contains more than 99% of all the mass in our solar system. Jupiter, that giant among planets, could swallow Earth more than 1,300 times over. Yet Jupiter itself represents less than 0.1% of the Sun's mass. The scale has already moved beyond what our senses can directly grasp. Think about standing somehow outside our solar system, looking back at this collection of worlds orbiting their star. Mercury appears as barely more than a dot. Mars shows itself as a rusty marble. Even giant Jupiter, with its swirling storms and dozens of moons, occupies just a tiny fraction of the space where planets can exist. Saturn's magnificent rings, stretching tens of thousands of kilometers, would look like gossamer threads around a distant ball. From this cosmic vantage point, our entire solar system begins to look like what it really is: a small neighborhood in a much larger city. The Sun that dominates our local experience becomes just one star among hundreds of billions in the Milky Way galaxy. An average star, neither particularly large nor particularly small. Just another point of light in an enormous spiral of stars, gas, and dust. But even calling our Sun average understates how strange stellar sizes can become. Red supergiant stars like Betelgeuse swell to dimensions that challenge comprehension. If you could somehow place Betelgeuse where our Sun sits, its surface would extend past the orbit of Mars. The entire inner solar system would exist inside this single star. Hypergiant stars push these boundaries even further. Ui Scuti, among the largest known stars, measures perhaps 1,700 times wider than our Sun. Light takes several hours just to travel across its diameter. These stellar giants burn through their fuel at incredible rates, living fast and dying young in cosmic terms. They represent one extreme of what a star can become, yet even they pale next to other cosmic structures. Black holes, those regions where matter has collapsed so completely that not even light escapes, can grow to masses billions of times greater than our Sun. They warp space-time itself, bending the very fabric of reality around their immense gravitational fields. Galaxies collect these stars, black holes, and clouds of gas into even grander structures. The Milky Way stretches roughly 100,000 light-years from edge to edge. Light itself, traveling at 300 million meters per second, needs 100,000 years to cross our galaxy. The nearest major galaxy, Andromeda, sits more than 2 million light-years away. Yet both galaxies are approaching each other, destined to merge in roughly 4.5 billion years. Galaxy clusters gather dozens or hundreds of galaxies together, across spans of millions of light-years. The Coma cluster contains over 1,000 known galaxies, bound together by gravity across a region roughly 20 million light-years wide. Dark matter, that mysterious substance we can detect only through its gravitational effects, provides the invisible scaffolding that holds these clusters together. But even galaxy clusters represent just the beginning of cosmic architecture. Superclusters link multiple galaxy clusters into chains and sheets that span hundreds of millions of light-years. The local supercluster, which contains our Milky Way, includes roughly 100 galaxy groups and clusters spread across more than 100 million light-years. These superclusters themselves organize into even larger structures. The cosmic web, as astronomers call it, reveals matter arranged in vast filaments, separated by enormous voids. Galaxy filaments stretch across billions of light-years, connected at nodes where superclusters form. Between these filaments lie cosmic voids, regions so empty that they contain almost no galaxies at all. The largest known structure bears the name of the astronomers who discovered it. The Hercules Corona Borealis Great Wall spans roughly 10 billion light-years across, making it larger than the observable universe was when it first formed. This structure challenges our understanding of how matter could organize itself on such scales so early in cosmic history. Yet even this immense structure might not represent the ultimate limit. The observable universe itself, that sphere of space from which light has had time to reach us, measures roughly 93 billion light-years in diameter. Beyond this boundary, more universe likely exists. Perhaps infinitely more, but we cannot observe it directly because light from those regions hasn't had time to travel to us. This raises fascinating questions about what we mean by largest. If the universe extends infinitely in all directions, then perhaps the concept of largest loses meaning entirely. You cannot have a largest thing in an infinite space, any more than you can have a largest number in mathematics. Every structure, no matter how vast, becomes infinitesimal compared to infinity. But maybe that's the point. Maybe the search for the largest thing isn't really about finding a final answer. Maybe it's about pushing our understanding to its limits, about discovering how far our minds can stretch before concepts break down entirely. The journey from mountain to ocean to planet to star to galaxy to supercluster to cosmic web represents more than just increasing size. It represents our species gradually learning to think beyond the scales that shaped our evolution. Consider how recent these discoveries are in human terms. Just over a century ago, most astronomers thought the Milky Way comprised the entire universe. The idea that other galaxies existed beyond our own seemed impossible. Today, we know of hundreds of billions of galaxies, each containing hundreds of billions of stars, organized into structures that span significant fractions of the observable universe itself. This expansion of knowledge continues accelerating. New telescopes reveal ever more distant and ancient structures. Computer simulations model the formation of cosmic architecture across billions of years. We're living through a golden age of discovery about the universe's largest scales, even as we struggle to comprehend what these scales actually mean. Perhaps the most remarkable thing about cosmic size isn't any particular structure, but rather how it makes us reconsider our place in existence itself. We emerged from a small planet, orbiting an ordinary star in an unremarkable galaxy, yet somehow we've developed minds capable of contemplating structures billions of times larger than anything in our direct experience. The atoms in our bodies were forged in stellar cores, scattered by supernovae, and eventually assembled into thinking beings who can ponder the very stars that created them. There's something almost magical about this connection between the very small and the very large. The quantum mechanics that governs subatomic particles somehow gives rise to chemistry, which enables biology, which produces consciousness, which contemplates cosmology. The largest structures in the universe exist because of processes that began at the smallest possible scales, in the first moments after the Big Bang. So when we ask about the largest thing in the universe, we're really asking about our own capacity for wonder. We're testing the boundaries of what minds like ours can grasp, can model, can imagine. Every answer we discover leads to new questions, larger scales, deeper mysteries. The universe seems designed to humble us, to remind us that no matter how much we learn, vastly more remains unknown. And maybe that's exactly as it should be. Maybe the question itself matters more than any final answer. Maybe the journey from human scale to cosmic scale teaches us something essential about curiosity, about the drive to understand, about our place in something far grander than we can fully comprehend. The largest thing in the universe might just be the mystery itself, forever expanding beyond our ability to contain it. Human measurement begins with the flesh we inhabit. Every judgment of size flows from the boundaries of our own bodies, the span of fingers, the reach of arms, the stride of legs. These became our first rulers. We carry this measuring stick wherever we go, comparing everything to the physical frame we know most intimately. For thousands of years, people could only conceive of largeness in terms they could touch or cross. Mountains represented the ultimate in height, because they challenged human endurance to climb. Oceans felt immeasurable, because crossing them tested the limits of survival. These were the edges of the comprehensible world, defined not by actual size, but by what human effort could overcome. Language preserves this ancient relationship between body and measurement. A foot was literally the length of a human foot, a yard stretched from fingertip to nose. Even our stories reflected this connection. Giants in mythology weren't alien creatures. They were humans scaled up, familiar forms stretched beyond normal proportions. When people needed to imagine something larger than life, they pictured it as something like themselves, only bigger. Ancient civilizations expanded these body-based measurements as they built their monuments. Egyptian pyramids still astonish us today, not just because of their height, but because they represent human labor multiplied beyond easy comprehension. Without machines, without engines, people moved blocks of stone that weigh more than most modern buildings. Size became a way to reach toward permanence, to create something that would outlast the fragile span of human life. The first major shift in human perspective came when sailors proved the Earth was round. Magellan's expedition in the early 1500s demonstrated that you could sail in one direction and eventually return to your starting point. The world, which had felt infinite, suddenly had boundaries. It was vast, but measurable. This revelation opened a door to a troubling question. If Earth has limits, what lies beyond those limits, and how large might that be? We still measure enormous distances in terms of human experience, though we rarely notice this habit. A road trip gets described in hours of driving. A flight to another continent gets measured in meals eaten and movies watched. Even space missions, the most extreme journeys we attempt, get anchored to timescales we understand. 3 days to reach the moon, several months to get a robot to Mars. Time becomes our bridge to understanding distance, because time is something we feel directly in our bodies. This is where pure mathematics entered the picture. Scientists needed ways to handle numbers that overwhelmed human intuition. A meter, you can visualize easily. A kilometer takes more effort, but you could walk one. 1,000,000 kilometers slips completely free from instinct. Scientific notation emerged as a solution, a way to write numbers like 10 to the 12th power, 10 to the 15th power, numbers so large that ordinary counting systems collapsed under their weight. Children demonstrate how we learn to handle big numbers. They start with fingers, then objects in a room, then abstract concepts like 1,000 students in a school, 1,000,000 stars in the sky. Beyond that point, numbers become more like names than experiences. We say billion, trillion, quadrillion, but few people can honestly picture what these words represent. This isn't a failure of imagination. It's simply that human brains evolved to deal with immediate environments, with tools and food and distances you could cross before sunset. The universe didn't design us to comprehend galaxies. We had to invent methods to stretch our understanding. Logarithmic scales, comparisons to light speed, metaphors that could fit cosmic enormity into sentences we could speak out loud. Even these mathematical tools get anchored back to human experience. Light years sound scientific and precise, but we still explain them through metaphors. If you could drive to the nearest star at highway speeds, the journey would take 50 million years. We return to travel time, because that's how our sense of largeness first developed. The drive to find the biggest of everything seems uniquely human. Other animals care about size only when it affects survival. A bird needs to know if a branch will support its weight. A predator judges whether its prey is larger or smaller than itself, but humans go further, seeking the tallest mountain, the deepest ocean, the largest whale. We seem compelled to test the edges of the possible, as if measuring size helps us understand our own place in the world. This curiosity deepened dramatically when we first saw Earth from space. Photographs taken in the 1960s showed our entire planet as a small blue marble floating in darkness, all the oceans, all the continents, all of human history contained in a sphere small enough to fit in a single image. What had felt infinite, a world without edges, was revealed as finite and surprisingly small compared to the blackness surrounding it. The human sense of big had to stretch once again. You might expect that once we had precise numbers and clear photographs, our understanding of size would stabilize. Instead, every improvement in our instruments pushes the definition of large even further out. Early telescopes revealed mountains on the Moon, storms on Jupiter, rings around Saturn. Better telescopes revealed other galaxies, then clusters of galaxies, then structures spanning billions of light years. Each discovery forces us to adjust our internal measuring stick, though the process often feels uncomfortable, even unbelievable. People once resisted the idea that Earth orbits the Sun because the claim felt too large to accept. Later generations resisted evidence of galaxies beyond our own. Now we discuss cosmic structures hundreds of millions of light years across, distances that cause our brains to simply give up trying to visualize them. We accept these scales not because we can feel them, but because our instruments provide evidence we trust more than our intuition. Education helps us cheat our way past the limits of instinct. Diagrams and models show the relative sizes of planets, stars, and galaxies through visual comparisons rather than direct experience. A child, looking at a poster of the solar system, learns not by walking between planets, but by comparing circles on paper. The human scale extends through metaphor and representation, symbols that stand in for relationships we cannot otherwise hold in our minds. Even these teaching tools often compress reality to make it manageable. Most diagrams of the solar system show planets far too close together, otherwise they wouldn't fit on the page. Space is mostly emptiness, but if you drew the distances to scale, the sun would be a dot on one wall, and the nearest planet would require another building to display. Our minds prefer compression over accuracy, though the truth is that the spaces between things often matter as much as the things themselves. Emptiness has size too, though it feels strange to acknowledge this fact. When we ask what is the largest thing in the universe, we're really asking something more fundamental about how we measure largeness at all. Is it what our bodies feel, what our eyes can see, what numbers can describe, or what images can convey? Each approach gives different answers, but all grow from the human scale we started with. Without our bodies as the first measuring stick, without our footsteps and lifespans as early references, we might never have developed curiosity about cosmic size in the first place. The human scale, limited as it is, provided the foundation for all our attempts to understand enormity. We extend an unbroken line outward, from fingers to continents, from planets to stars, from stars to galaxy clusters and beyond. Every step in this progression builds on the original foundation of human measurement, the unconscious ruler we carry in our flesh and bones. When we try to grasp what truly enormous means, our thoughts naturally drift to the towering giants right beneath our feet. Long before humans pointed telescopes at distant stars, long before we understood that those tiny lights were actually massive suns, the most incredible comparisons lived right here, on Earth. The peaks that seemed to touch the heavens, the waters that vanished beyond every horizon. These were the titans that first taught us about of overwhelming size. Even today, with all our knowledge of galaxies and cosmic distances, these earthly monsters remain our first teachers about natures. There's something profound about standing next to a mountain, feeling your own body shrink in comparison. The very air changes as you climb higher. Weather systems behave completely differently at the summit than they do in the valleys below. Snowcaps gleam in sunlight, while warm breezes blow through the foothills thousands of feet below. These geological giants aren't just piles of stone reaching skyward. They're complex machines that shape entire climates, control water systems, create countless different environments from dense forests to pristine glaciers, all stacked vertically in one magnificent structure. For someone who's never witnessed a real mountain, the concept almost defies belief. This massive wall of earth and rock rises impossibly high, yet somehow, with enough determination and time, humans can actually climb over it. Consider Mount Everest, our planet's highest point above the ocean's surface. Nearly 9 kilometers of vertical rock and ice. It pushes human bodies to their absolute breaking point. The atmosphere near its peak holds roughly 1/3 the oxygen we breathe at sea level. Every single step becomes a monumental effort. Every breath feels inadequate and shallow. Climbers must carry pressurized oxygen just to survive in that alien environment. From our human perspective, Everest isn't merely a mountain, it's practically another world, so extreme that life barely manages to exist there. Yet when we zoom out to consider Earth as a whole, this massive peak becomes nothing more than a tiny bump. If you could shrink our entire planet down to the size of a smooth billiard ball, even the highest mountains and deepest valleys would feel completely smooth to your fingertips. Earth's total diameter measures about 12,700 kilometers. Everest reaches less than 9 kilometers high. On that reduced scale, our tallest peak amounts to barely a scratch on the surface. This comparison offers one of the most important lessons about understanding true scale. What feels impossibly massive when you're standing right next to it becomes practically invisible when viewed against the bigger picture. Everest overwhelms us precisely because our bodies are so small in comparison, but to Earth itself, this mountain barely registers as a feature. This same principle applies everywhere we look. The oceans teach us identical lessons about perspective and scale. The Pacific Ocean represents the largest single feature covering our planet's surface. Spreading across more than 160 million square kilometers, it contains more water than every other ocean combined. Modern ships require weeks to cross its expanse. Aircraft need many hours of continuous flight. Throughout most of human history, this vast body of water remained completely unknown, appearing on maps as blank spaces marked with warnings and guesses. Entire civilizations have lived and died without ever glimpsing its far shores. Standing on any Pacific beach and staring toward that endless horizon creates an almost overwhelming sense of infinity pressing against your consciousness. No matter how far you travel across its surface, that line where water meets sky always remains exactly the same distance away, creating the illusion that the ocean continues forever in every direction. But oceans, like mountains, can also be put into proper context. The Pacific averages roughly 4 kilometers deep across its entire expanse. At its most extreme point, the Mariana Trench, It plunges nearly 11 kilometers straight down into absolute darkness. That's actually deeper than Everest is tall. If you could somehow drop our highest mountain into that deepest trench, its peak would still sit more than a full kilometer underwater. Trying to visualize that much vertical space, filled entirely with crushing darkness and unimaginable pressure, creates an unsettling feeling in most minds. At those incredible depths, water pressure becomes more than 1,000 times greater than what we experience at sea level. Enough crushing force to completely destroy ordinary submarines like empty cans. Yet even in these seemingly impossible conditions, life finds ways to adapt and thrive in a world that never sees sunlight. Earth's giants aren't just tall or wide, they're also incredibly deep, extending into environments where humans can barely survive even with advanced technology. Mountains and oceans appear together constantly in human myths and stories because they represent perfect opposites. One reaches desperately toward the sky, the other sinks into mysterious hidden depths. Mountains can be seen from incredible distances. Oceans conceal their true immensity beneath deceptively calm surfaces. Both serve identical roles in human imagination, reminding us that our sense of size depends entirely on what we're comparing things to. Any mountain towers over a human climber, but from space it looks like a gentle ridge. An ocean feels infinite to someone sailing across it, but from orbit it appears as just a blue patch on a spinning globe. The crucial lesson here is that immensity isn't some absolute quality. It depends completely on perspective, on your frame of reference, on what you're measuring against. It's worth imagining what that moment must have felt like for the first humans to reach Everest's summit. In 1953, Edmund Hillary and Tenzing Norgay stood at the highest point on Earth's surface. For that brief moment, no other human being had ever stood higher while remaining on solid ground. Their view stretched for hundreds of kilometers across other peaks that were themselves taller than anything found on other continents. Yet above them, the sky continued infinitely upward. Even at our planet's highest point, they were only about 1/3 of the way to where commercial aircraft routinely cruise. Beyond that lies space, and beyond space, the stars. Our highest mountain still leaves us remarkably close to the ground. Now picture those first explorers who dared to cross the Pacific's immensity. Polynesian navigators steered their small canoes across thousands of kilometers, using only stars, wind patterns, and ocean currents as guides. They set out without seeing any land ahead, trusting knowledge that had been passed down through countless generations. To these remarkable people, the ocean wasn't just large, it was a living map, a constantly changing field of motion and patterns that could be read like text. For months they might travel without touching any shore, yet still know exactly where they were by reading the sky above and the water below. The Pacific, immense as it truly is, became knowable through patience, skill, and deep understanding. These stories reveal something profound about humanity's relationship with size and scale. What we call large isn't only about raw numbers and measurements. It's about effort, about difficulty, about what can or cannot be accomplished within a human lifetime.
Everest feels enormous because it pushes our bodies beyond their comfortable limits. The Pacific feels vast because crossing it demands weeks or months of continuous travel.
Size isn't just geometry and mathematics, it's lived experience. That's exactly why mountains and oceans continue feeling enormous even after we know their precise measurements. They challenge us, test our limits, and that challenge makes them feel genuinely big. But when we step back to observe Earth from a distance, their immensity suddenly shrinks dramatically. Our tallest mountain measures less than 0.1% of the planet's total diameter. The deepest ocean trench represents an even smaller proportion. Our largest ocean covers just under 1/3 of the surface area. From the perspective of space, Earth appears remarkably smooth and uniform. Clouds, continents, and seas blur together into gentle patterns. All those wrinkles that create our sense of awe completely vanish into the simple curve of a sphere floating in darkness. This dramatic shift in perspective represents part of the journey toward truly understanding scale. Earth's giants are only giants from our limited viewpoint. They serve as valuable practice, teaching us how quickly something large can fade into insignificance when we widen our frame of reference. This lesson becomes even more striking when we shift our attention from surface features to the planet as a complete system. While mountains and oceans once defined the absolute limits of human imagination regarding size, Earth itself certainly isn't the end of this story. It's simply the next comparison waiting for us. Just another ball of rock and water that gets completely dwarfed by what lies beyond in the vast darkness of space. Earth stretches about 12,742 kilometers across at its widest point. That's a number that might sound abstract until you imagine walking it. Step by step, around the equator you'd cover roughly 40,000 kilometers before returning to where you started. Walking 8 hours every day, without rest, without obstacles, without oceans blocking your path, you'd need more than a year to complete that journey. The sheer scale becomes almost incomprehensible when you think about it. Most people throughout history never saw more than a tiny fraction of our planet's surface. The world felt infinite to them, vast enough to hide entire continents on the far side. Mysterious enough that whole civilizations could exist without knowing about each other. Early explorers learned this lesson the hard way. They set out thinking they could measure the Earth in days or weeks of travel. Instead, they discovered that crossing our planet demanded months, years, sometimes entire generations of effort. The world simply refused to be small, but perspective changes everything. When you step back and look at Earth from space, those vast distances start to seem much more manageable. The Moon sits about 384,000 kilometers away from us. That's roughly 30 times Earth's diameter. If you shrunk our planet down to the size of a marble, about 2 centimeters across, the Moon would be about the size of a pea, orbiting 30 centimeters away. Suddenly, our entire Earth-Moon system fits neatly on a tabletop. This shift in perspective became real when astronauts first left our atmosphere and looked back. They saw something that no human had ever seen before. Earth appeared as a small glowing sphere suspended in the darkness of space. The famous blue marble photograph from 1972 captured this view perfectly. Every human being, every memory, every story that had ever existed, compressed into a ball small enough to fit inside a single frame. That image changed how we think about our world. Down here on the surface, Earth still feels vast, still holds mysteries in its far corners. But from space, it looks fragile, finite, surprisingly tiny. You realize that all of human history, all of our wars and achievements and dreams, have played out on this one small stage, floating in an ocean of emptiness. The feeling of smallness grows even stronger when you compare Earth to its planetary neighbors. Jupiter stretches 11 times wider than our world. It's over 300 times more massive. Saturn, nearly as wide, wears rings that extend hundreds of thousands of kilometers into space. Even the ice giants, Neptune and Uranus, make Earth look like a minor player in our solar system. Among all the planets orbiting our Sun, Earth sits somewhere in the middle of the size range. Bigger than Mars and Mercury, much smaller than the gas giants. It's almost as if it found the perfect balance, just large enough to hold onto an atmosphere and liquid water, just small enough to avoid becoming a swirling ball of gas like Jupiter. This size isn't random, it's crucial. Too small, and Earth wouldn't have enough gravity to keep air molecules from drifting away into space. Too large, and we might have ended up as another gas giant. Our planet's diameter isn't just a measurement, it's a condition that makes life possible. The Sun dwarfs even Jupiter. Its diameter stretches about 109 times wider than Earth. You could line up more than 100 Earths across the Sun's face. Over 1 million Earths could fit inside its volume. From our perspective down here, the Sun looks like just a disk in the sky, something you can block with your thumb at arm's length. But in reality, it's the colossus of our solar system, and Earth is just a small companion, circling at a safe distance. We don't usually think about the Sun this way, because it's constant in our lives, rising and setting each day like clockwork. But the scale difference is overwhelming. Earth is barely a detail compared to our star. Yet this vast size difference is precisely what keeps us alive. The Sun needs to be enormous to generate the energy that reaches us across 150 million kilometers of space. Earth's size shapes our experience of time itself. A day lasts 24 hours because that's how long it takes our planet to spin once on its axis. A year contains 365 days because that's how long Earth takes to orbit the Sun. These rhythms are anchored to our planet's dimensions and speed. Change Earth's diameter, and those rhythms would change too. A larger planet might spin more slowly, giving us longer days. A smaller one might spin faster, making days rush by. Every clock we build, every calendar we write, echoes our planet's size. The way we measure time is fundamentally connected to the scale of the world beneath our feet. It's a reminder that our human experience is tied to the cosmic mechanics of a ball of rock spinning through space. The question of Earth's true smallness becomes almost overwhelming when you consider the observable universe. Space stretches about 93 billion light-years across. That number is so large it breaks our ability to comprehend it. If you shrunk Earth down to the size of a grain of sand, the observable universe would still be larger than Earth itself compared to that tiny grain. This comparison is deeply humbling. It shows us that even a whole planet, full of mountains and oceans and forests and cities, is essentially a speck in a much grander scheme. Earth contains everything we know, every landscape we've ever seen, every culture that has ever existed. And yet, from the perspective of the cosmos, it's almost invisible, but size isn't the same as significance. Earth may be small compared to Jupiter or the Sun. It may almost disappear when compared to the universe, but it's also the only place we know that holds beings capable of asking about size at all. This creates a fascinating paradox. Our world is small in measure, but vast in meaning. It's a tiny stage that somehow produced consciousness capable of contemplating its own teeniness. Earth's particular size shapes everything about its character. The planet's mass allows it to retain heat deep in its core. This molten interior drives plate tectonics, the slow dance of continents that builds mountains and opens oceans over millions of years. Our world is large enough to keep its interior active, creating the geological processes that constantly reshape the surface. Gravity, determined by Earth's mass, holds our oceans in place and prevents our atmosphere from drifting away into space. The escape velocity from Earth's surface is high enough to keep most gases from leaving, but not so high that we're trapped under a crushing atmosphere like Venus. This balance gives us weather systems, the cycling of water and carbon, the dynamic environment that life depends on. If Earth were much smaller, it would be geologically dead, like Mars. If it were much larger, it might have a crushing atmosphere of hydrogen and helium like Neptune. Our planet's size sits in a narrow range that allows for complexity, for the intricate dance of water and rock and air that creates a living world. Looking outward into space, we now know that planets are incredibly common. Over the last few decades, astronomers have discovered thousands of worlds orbiting other stars. Some are rocky and small, others are giant and gaseous. Planets might be the most common type of object in the universe, after stars themselves. In that sense, Earth is just one among countless billions of worlds, scattered throughout the galaxy. But when you think about the specific conditions needed for life, the sense of rarity returns. Earth's size, its distance from the Sun, its balance of land and water, the presence of a large moon to stabilize its rotation. These details transform it from just another ball of rock into something far more remarkable. A world capable of harboring consciousness, of producing beings that can measure and contemplate the very cosmos they inhabit. That combination may be far rarer than size alone would suggest. When you think about our planet Earth, imagine holding an apple in your hands. Now picture that apple as our entire world. The atmosphere that surrounds us, that keeps us alive and breathing, would be thinner than the waxy coating on that apple's skin. This comparison alone reveals something profound about the nature of our existence. Every mountain we consider towering, every peak that challenges climbers and inspires poets, would appear as nothing more than a barely noticeable bump on that apple. Mount Everest, the Himalayas, the Rocky Mountains, all of them would vanish into smoothness when viewed from this perspective. The deepest parts of our oceans, those mysterious trenches that plunge kilometers down into darkness, would be mere scratches on the surface. This fragile shell that contains everything we know as life, this biosphere, extends only a few kilometers deep into the oceans and a few kilometers high into the sky. When you consider that Earth's radius measures over 6,000 kilometers, you start to realize just how thin this layer of existence really is. Every plant, every animal, every human being that has ever lived fits within what would appear as an almost invisible film on our apple-sized planet. Standing here on solid ground, though, none of this feels small or fragile. The horizon stretches away from us, hiding whatever lies beyond that line, where Earth meets sky. A journey across continents takes weeks of travel. Oceans seem to go on forever when you're sailing across them. Our eyes can only see small pieces at a time, so our minds must work to imagine the whole picture. This limitation of human perspective changed dramatically when we first saw photographs of Earth taken from space. Those images shattered the illusion that our world goes on endlessly. Suddenly, we could see that our planet has edges, has limits, has a definite size. The Earth revealed itself as finite, bounded, complete. These space images set up a fascinating contradiction in how we understand scale. Earth measures a little over 12,000 kilometers across, which sounds enormous until you compare it to other worlds. Jupiter stretches 140,000 kilometers from edge to edge. Our Sun spans nearly 1.5 million kilometers. Some stars grow even larger than our Sun. Each step outward in these comparisons makes Earth seem smaller, but also somehow more precious. As the scales grow larger and larger, the number of places where life might exist seems to shrink. We find ourselves surrounded by immensity, while our home remains a small, fragile sphere floating in that vastness. This creates two perspectives that we carry with us simultaneously. First, Earth feels large compared to human scale, full of features that challenge our endurance and stretch our imagination. Second, Earth appears small compared to almost everything beyond it. These two viewpoints exist together, creating a strange tension in how we understand our place. When we move beyond Earth and start comparing it to other planets in our solar system, the meaning of size transforms into something entirely new. Our world, impressive to us in every possible way, becomes just one among many worlds circling our Sun. More humbling still, it's not even the largest of these worlds. Jupiter stands as the most obvious example of planetary scale that dwarfs our own. Its diameter reaches about 142,000 kilometers, more than 11 times Earth's width. If you imagine Earth shrunk down to the size of a grape, Jupiter would be closer to a basketball sitting next to it. You could line up more than a dozen Earths across Jupiter's face and still have empty space left over. The volume comparison becomes even more staggering. Jupiter could contain over 1,300 Earths inside its bulk. Try to imagine every continent, every ocean, every mountain range on our planet, then multiply that by more than 1,000. All of that would still fit inside Jupiter's volume. These numbers stretch beyond what our minds can easily grasp, but Jupiter differs from Earth in fundamental ways beyond just size. It's not solid like our rocky planet. Instead, Jupiter is a gas giant, composed mostly of hydrogen and helium, with no clear boundary between its atmosphere and whatever lies deeper inside. You couldn't stand on Jupiter's surface because it doesn't have a solid surface to stand on. As you traveled deeper into Jupiter's layers, the gas would become denser and hotter around you. Eventually, the pressure would become so intense that hydrogen atoms get squeezed into a form called metallic hydrogen, where they conduct electrical current like metal does. The physics of this transformation happens under conditions so extreme they're difficult to recreate on Earth. Jupiter's mass exceeds Earth's, by more than 300 times, yet its density is much lower than our planet's. The material that makes up Jupiter is spread out over such an enormous volume that the planet is actually less dense than Earth, despite being so much more massive. This low density reveals something interesting about Jupiter's nature. If Jupiter had gathered just a bit more mass during its formation, it might have ignited nuclear fusion and become a star instead of a planet. In some ways, Jupiter represents a failed star, something caught between being a planet and being something much more significant. This borderline status adds another layer to thinking about scale and what different sizes mean in cosmic terms. One of Jupiter's most famous features is a storm system called the Great Red Spot. This single storm is larger than our entire planet Earth. The winds in this vortex have been raging for at least 350 years, possibly much longer. Some astronomers think this storm might have been spinning for centuries before humans first observed it through telescopes. Imagining weather systems that can be larger than planets and that can persist longer than entire civilizations gives us a glimpse into what time means on Jupiter's scale. On Earth, storms are measured in days or weeks. Even the most persistent weather patterns rarely last more than a season. On Jupiter, storms can be measured in centuries. Time itself seems to operate differently when you're dealing with such massive scales. Saturn offers another perspective on what planetary immensity means. Its diameter spans about 120,000 kilometers, slightly smaller than Jupiter, but still nearly 10 times Earth's width. Saturn's mass equals about 95 Earths, and its volume could hold over 700 of our worlds inside it. Yet Saturn is even less dense than Jupiter. In fact, Saturn is the least dense planet in our entire solar system. If you could somehow find a bathtub large enough, Saturn would actually float in water because its average density is less than water's density. This fact alone demonstrates how different these gas giants are from the rocky planets we're familiar with. Saturn's low density isn't just a measurement curiosity. It reveals something fundamental about what planets can become when they grow past certain scales. Size becomes not just about measurement, but about composition, about what a world can be when it accumulates enough material to transform its very nature. Saturn possesses something that makes it unique among all planets, its magnificent ring system. While Jupiter, Uranus and Neptune also have rings, theirs are faint and difficult to see. Saturn's rings are immense, bright, and unmistakable. They stretch outward more than 280,000 kilometers from the planet's center, wider than the distance between Earth and our moon. These rings appear substantial from a distance, but they're astonishingly thin, only a few dozen meters thick in most places. They consist of billions of particles of ice and rock, ranging from tiny grains to chunks the size of houses. All these fragments orbit Saturn in a perfectly flat plane, each one following gravity's rules in precise order. From far away, the rings look like solid bands circling the planet. Up close, they reveal themselves as a delicate dance of countless fragments, each piece maintaining its own orbit while contributing to the overall pattern. This creates a structure that's both immense in reach and delicate in construction. The rings aren't permanent features. Astronomers believe they formed relatively recently, perhaps only 100 million years ago, when a moon or comet got torn apart by Saturn's powerful gravity. The rings may also fade in the distant future as particles either fall inward towards Saturn or drift away into space. For now, though, they represent one of the most striking sights in our solar system. When spacecraft send back detailed images of Saturn's rings, they look like lace stretched across space, immense in their reach yet delicate in their thickness. This reminds us that size isn't always about bulk or mass. Sometimes scale is about spread, about reach, about how even thin structures can create awe when they extend far enough. Comparing Jupiter and Saturn to Earth shows us that size operates in multiple dimensions. Earth has solidity, a surface you can walk on, a density that makes it feel familiar and substantial. Jupiter and Saturn have bulk and volume, but they're diffuse and gaseous, more like layered atmospheres wrapped around cores we cannot directly observe. Their immensity comes not from being solid giants, but from being swollen with light elements. Their gravity strong enough to hold vast amounts of material together, despite low overall density. When we call them large, we mean when we call Earth large. These giant planets also remind us that moons can be part of the story of planetary scale. Jupiter has more than 90 known moons orbiting around it. Saturn has more than 80. Some of these moons are larger than Mercury, which we consider a full planet in its own right. Ganymede orbiting Jupiter is the largest moon in our solar system, stretching over 5,200 kilometers across. Titan, Saturn's largest moon, is nearly as big and has a thick atmosphere, plus lakes filled with liquid methane. If these moons orbited the Sun independently, we would classify them as planets without hesitation. These giant planets carry entire miniature solar systems along with them. Each system has its own scale of worlds, its own collection of bodies with different sizes, compositions, and characteristics. The concept of planetary size spreads outward again, becoming more complex as we realize a planet isn't just a single body. It's a gravitational center that can hold dozens of companions, each one adding to our understanding of what scale means. Jupiter and Saturn might seem like ultimate examples of planetary size, but even they have limits. Compared to our Sun, they appear small. Compared to larger stars, they become tiny. Still, within our solar system, they completely redefine what it means for a planet to be immense. They show us that Earth, while incredibly rich in detail and complexity, is modest when it comes to sheer size. These comparisons remind us that scale has layers upon layers. What feels all-encompassing to us can be dwarfed by something larger, and the journey toward understanding size is always about what you place beside what. Context determines whether something seems large or small. As we examine Jupiter's mass and Saturn's ring systems, we see how words like giant shift depending on perspective. To a person standing at its base, Mount Everest is a giant. To planet Earth, Everest is just a small bump on the surface. To Earth, Jupiter appears as a giant. To Jupiter, Saturn represents a rival. To our Sun, both planets are relatively small objects. Each comparison pushes the scale outward, each step preparing us for the next level, where even these massive planets fade into the background against the immensity of stars. This ladder of size keeps climbing upward, and the rungs are always farther apart than we initially expect them to be. Our solar system appears as this magnificent collection of worlds, each one carrying its own personality, its own colors and moods. But here's something that might shift how you see it all. Despite Jupiter's massive presence, despite Saturn's elegant rings stretching into space, all these planets are really just the supporting cast in a much grander performance. The Sun isn't simply another member of our cosmic neighborhood. It basically is the neighborhood. Nearly every single thing we experience, every aspect of life as we know it, gets shaped by this one central presence. Its enormous size, its relentless heat, the invisible pull of its gravity, all working together to orchestrate everything around it. When you really start to grasp the Sun's actual scale, even Jupiter starts looking like a marble next to a basketball. We're talking about something that stretches 1.4 million kilometers across. Picture this. If you lined up over 100 Earths side by side, they would just barely span the Sun's width. And that's just thinking in 2 dimensions. If we're talking volume, you could hollow out the Sun and stuff more than 1 million Earths inside. Every mountain range, every deep ocean, every sprawling city, every person who's ever lived, all of that could fit inside with room to spare. It transforms our entire planet into something like a pebble orbiting around a bonfire. The strangest part is how the Sun manages to look so ordinary from down here. Day after day, it shows up as this bright circle, appearing no bigger than the moon to our eyes. This happens because distance plays tricks on our perception. The Sun sits about 150 million kilometers away from us. That's so far that light itself, the fastest thing in the universe, takes 8 full minutes to make the journey. Think about that for a moment. If the Sun just vanished right now, this instant, we'd still see daylight for 8 more minutes before darkness finally arrived. Distance has this way of making the impossible seem manageable, the enormous seem small. But the sun's mass tells an even more incredible story. It accounts for more than 99% of everything in our solar system. All the planets, all the moons, every asteroid tumbling through space, every comet with its glowing tail, all of that combined makes up less than 1% of the total mass here. In other words, our solar system is basically the sun with some cosmic dust sprinkled around it. Jupiter might seem enormous to us, but compared to the sun, it's only about 1,000th of its mass. All the planets together are like specks of dust clinging to the edge of something vast beyond imagination. Without the sun's tremendous gravitational pull, there would be no solar system at all. The planets would just drift off into the galaxy like seeds carried by an invisible wind. The sun operates as a star, which means it's essentially a sphere of superheated plasma, powered by nuclear fusion happening deep in its core. Hydrogen atoms get squeezed together under pressure so intense, it's hard to even imagine forming helium in the process. This releases energy, constantly, relentlessly. Every single second, the sun converts about 600 million tons of hydrogen into 596 million tons of helium. Those missing 4 million tons don't just disappear, they get transformed into pure energy, radiating outward as light and heat. This process has been going on for roughly 4.6 billion years, and it'll continue for billions more. To us, the sun seems constant, reliable, unchanging. But in reality, it's this vast furnace burning through unimaginable amounts of fuel every instant, sustaining itself through sheer scale alone. The light touching your face right now began as energy deep inside the sun's core, and it took an extraordinary journey to reach you. Particles of light, called photons, bounce around inside that dense plasma for thousands, sometimes millions of years. They scatter in every direction, gradually working their way outward through the sun's layers. By the time they finally reach the surface and escape into space, they've been delayed and deflected countless times. The sunlight warming your skin today might have begun its journey long before humans even existed on Earth. Once it finally leaves the sun's surface, it crosses the distance to our planet in 8 minutes, then continues outward across the galaxy, reaching planets and moons and spacecraft scattered throughout space. The sun is large, not just in terms of space, but also in terms of time. Its processes stretch across scales that make human history seem like a brief moment. The sun's surface, what scientists call the photosphere, reaches about 5,500 degrees Celsius. That's hot enough to instantly vaporize any material we know of on Earth. But here's something puzzling. The sun's outer atmosphere, called the corona, gets far hotter, reaching millions of degrees. How can the outer layer be hotter than the surface itself? Scientists think magnetic fields might transfer energy outward in ways we don't fully understand yet. It reminds us that size isn't just about physical dimensions, it's also about the vastness of energy, extremes of temperature, the reach of influence. One way to really feel the sun's scale is to consider its storms. Sunspots are regions of intense magnetic activity, cooler than the surrounding surface but still thousands of degrees hot. Some sunspots grow so large that Earth could fit inside them entirely. Solar flares, sudden releases of energy from the sun's surface, blast radiation across the entire solar system, sometimes interfering with our satellites and communication systems. Coronal mass ejections represent even more dramatic events. These vast eruptions of plasma send billions of tons of charged particles hurtling outward at millions of kilometers per hour. When these particles strike Earth's magnetic field, they create auroras, those shimmering curtains of light that dance across polar skies. These aren't minor disturbances we're talking about. They're storms on a scale that makes our hurricanes and earthquakes seem small by comparison. The sun's activity shapes what we call space weather, influencing the environment around planets millions of kilometers away. When you compare our sun to other stars in the galaxy, its size takes on different meaning entirely. In astronomical terms, the Sun is actually pretty ordinary. It gets classified as a G-type main sequence star, one of the most common categories out there. There are stars far smaller, like red dwarfs, barely large enough to sustain fusion. And there are stars far larger, like red supergiants, whose diameters can be hundreds of times greater than our Sun's. By cosmic standards, our Sun is average, maybe even modest. But for us, it defines everything. Its size determines our days, our seasons, our entire sense of time itself. Without the Sun, Earth would be nothing but a frozen rock drifting in darkness. Its enormousness to us isn't just about diameter or mass. It's about centrality, indispensability, its role as the anchor of everything we know. The Sun shows us that size is always relative to perspective. To a human being, it's enormous beyond words. To an astronomer comparing different stars, it's typical. To the galaxy containing hundreds of billions of stars, it's just a single point of light. Yet, its ordinariness is exactly what makes it so valuable. An average star with a stable lifespan provides just the right conditions for planets like Earth to exist. If the Sun were much larger, it would burn brighter, but live much shorter, consuming its fuel in tens of millions of years instead of billions. That wouldn't have left enough time for life to evolve and develop. If it were smaller, Earth might be too cold, permanently locked in ice. The Sun's size, ordinary in cosmic terms, turns out to be extraordinary in its balance. Throughout human culture, the Sun has always represented power, warmth, and life itself. Ancient civilizations worshipped it as a god. Farmers measured their seasons by its rising and setting. Even today, its presence defines our days, our calendars, our very sense of time passing. Its largeness isn't only physical, but also symbolic. It's the thing we depend on most without really thinking about it. The constant presence that shapes our lives invisibly. That represents another kind of size entirely, the size of significance. When we remember that the Sun's energy is what allows Earth to be what it is, we realize that the Sun's immensity is also ours, in a way. Every breath of oxygen results from plants using sunlight to split carbon dioxide and water. Every bite of food represents a chain of energy that begins with photosynthesis. Even fossil fuels are really ancient sunlight, stored by plants millions of years ago. Our bodies get powered by the Sun in the most literal way possible. Its size isn't distant from us, it's within us every day, in every heartbeat. As we stand here looking up at what appears to be a bright disk in the sky, it's easy to forget we're actually staring into a nuclear furnace. Easy to forget that this star radiates energy across the void, shaping space for billions of kilometers in every direction. Easy to forget that this Sun, so central to our existence, is actually ordinary compared to some stars out there. Stars so immense that even our Sun shrinks by comparison. From the gentle warmth on your skin to Jupiter's distant orbit, the Sun defines scale in our little corner of space. But like every step in understanding the universe, what seems ultimate now will eventually be overshadowed by something even larger, even more magnificent. Looking up at the night sky, we're actually staring at an endless collection of suns. Each tiny dot of light is a massive ball of fire, burning with incredible intensity. The only reason our Sun seems special is because it happens to be close to us, but really, it's just one star among billions and billions of others. Stars exist in sizes that completely break our normal understanding of scale. The smallest ones, called red dwarfs, might seem tiny by stellar standards, but they're still absolutely enormous. Even the most modest red dwarf dwarfs our entire planet, Jupiter. These little stars, if we can call them that, burn their fuel so slowly that they'll outlive almost everything else in the universe. They'll keep shining for trillions of years, long after our Sun has died out. Then there are the monsters, stars so big that they make our Sun look like a pebble. Take Betelgeuse, that reddish star you can spot in Orion's shoulder. If you somehow moved it to where our Sun sits, its surface would stretch all the way past Mars. The entire inner solar system would be inside this single star. But Betelgeuse isn't even close to being the biggest. There are hypergiant stars out there, with names like VY Canis Majorices, that are nearly 2,000 times wider than our Sun. Put one of those where our Sun is, and it would swallow up everything, all the way out to Jupiter, or even Saturn. The scale is so massive that it becomes almost meaningless to our everyday experience. What's fascinating about stellar size is how it connects to time itself. The biggest stars, those incredible hypergiants, burn through their fuel like there's no tomorrow. They might only live for a few million years, which sounds like a long time to us, but it's basically nothing in cosmic terms. Meanwhile, those tiny red dwarfs, they're so efficient that they'll keep burning long after our galaxy has changed completely. Our Sun sits right in the middle of this size spectrum. Not too big, not too small. It's been burning steadily for about 4.5 billion years, and it's got another 5 billion or so left in it. That middle ground, that perfect balance, is exactly what allowed life to develop here on Earth. The energy these stars pump out is almost impossible to grasp. Every single second, our Sun releases more energy than humans have used in our entire existence as a species. And remember, our Sun is just average-sized. The really big stars, they're putting out thousands of times more energy than that. Imagine planets orbiting those giants, getting blasted with radiation so intense that the very atoms in their atmosphere get stripped away. Stars don't usually live alone either. Many of them exist in pairs, slowly dancing around each other in gravitational embraces that last for millions of years. Sometimes these binary systems get so close that one star actually steals material from its partner. Gas flows between them like a cosmic river, creating some of the most beautiful and violent phenomena in space. Then you have star clusters, where hundreds or thousands of stars all hang out together, bound by their mutual gravity. If Earth somehow ended up inside one of these clusters, our night sky would be filled with dozens of stars as bright as our moon. You could probably read a book just from starlight alone. But here's where things get really mind-bending. Despite all this incredible scale, despite stars being so massive that they can fit millions of Earths inside them, they're actually just the building blocks of something even larger. Galaxies are made up of hundreds of billions of stars, all swirling together in vast spiral arms or elliptical clouds. Our Milky Way galaxy contains somewhere between 200 and 400 billion stars, each one potentially a sun to its own collection of planets. Some of those stars are red dwarfs that will outlive everything else. Others are massive giants, burning bright and fast, destined to explode in spectacular supernovas. The distances between stars are so vast that light itself, the fastest thing in the universe, takes years to travel from one to another. The nearest star to our Sun would take our fastest spacecraft tens of thousands of years to reach. And that's just our closest neighbor. When you really think about it, the existence of stars forces us to confront just how small our daily concerns actually are. We worry about things happening in our cities, our countries, maybe our planet. But out there are stellar furnaces burning with the energy of billions of hydrogen bombs every single second. Some of them have been doing this since before Earth even existed. The elements that make up our bodies, the carbon, oxygen, and iron flowing through our veins, were actually forged inside ancient stars. When those stars reached the end of their lives, they scattered these elements into space, where they eventually came together to form new stars, new planets, and eventually us. In a very real sense, we are made of star stuff. Every star we can see with our naked eyes is within our local galactic neighborhood. But there are other galaxies, billions of them, each containing their own hundreds of billions of stars. The total number of stars in the observable universe might be larger than the number of grains of sand on every beach on Earth. And yet, for all their immensity, stars followed the same basic physical laws that govern everything else. Gravity pulls their matter inward, while nuclear fusion pushes outward. It's a constant battle between collapse and explosion. that can last for billions of years. The same force that makes an apple fall is what keeps these massive furnaces burning in perfect balance. Perhaps what's most remarkable about stars is that despite their incredible size and power, they're also incredibly organized. They're not random explosions of energy. They're steady, predictable, reliable sources of light and heat. They follow patterns. They have life cycles. They interact with each other in ways we can understand and even predict. This organization at such massive scales suggests something profound about the universe itself. Even at sizes that completely dwarf human experience, there's still order, still structure, still rules that everything follows. The universe isn't chaotic, it's just operating at scales we're only beginning to comprehend. Stars exist in a vast range of sizes, and when you really start looking at the numbers, the differences become almost impossible to grasp. Our sun feels enormous to us, this blazing ball of fire that dominates our sky, but in the grand scheme of stellar sizes, it's actually quite average. There are stars so small, they barely glow, red dwarfs that smolder quietly for trillions of years, burning their fuel so slowly they'll outlive almost everything else in the universe. Then there are the giants, the red supergiants, and hypergiants that make our sun look like a pebble next to a basketball. These stellar monsters can be hundreds, even thousands of times wider than our sun. The sheer scale starts to break down our normal ways of thinking about size. Take Betelgeuse, that reddish star you can see in Orion's shoulder on a clear night. It's sitting about 640 light-years away, looking like just another dot of light. But if you could somehow place it where our sun is, its surface would stretch out past Mars, maybe even brushing against the asteroid belt. Instead of looking up and seeing our familiar sun, you'd see a red dome covering half the sky. The very idea of it makes you realize how small our perspective really is. But Betelgeuse isn't even close to being the largest star we know about. There's Scuti, which is roughly 1,700 times wider than our sun. If you put it at the center of our solar system, its surface would extend beyond Jupiter's orbit. We're talking about a single star that could swallow thousands of suns. At some point, the numbers become so large they stop meaning anything concrete. They just become symbols of incomprehensible vastness. These giant stars burn through their fuel at incredible rates, while our sun will keep burning for about 10 billion years total. These hypergiants might only last a few million years. They live fast and die spectacularly, often exploding as supernovas that can outshine entire galaxies for weeks or months. There's something almost tragic about these stellar giants. Their immense size is both their glory and their downfall. They start life as stars not too different from our sun, just more massive. But as they age, they begin to swell, their outer layers expanding outward, while their cores contract and heat up. The surface temperatures drop, giving them that characteristic red color, while inside, the core gets hot enough to fuse heavier and heavier elements. This process of stellar aging reveals something profound about how the universe works. These dying giants are actually cosmic factories, creating the elements that make up rocky planets and living things. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was forged in the nuclear furnaces of massive stars like these. When they explode, they scatter these elements across space, seeding the next generation of stars and planets. It's remarkable to think that from Earth, even these enormous stars look like tiny points of light. Distance has a way of equalizing everything, making the largest objects in the universe appear no different from much smaller ones. You need careful measurements and sophisticated instruments to reveal their true nature. This teaches us something important about perception and reality, how the most impressive things in the universe can hide in plain sight. The cores of these giant stars become laboratories for extreme physics. Temperatures reach hundreds of millions of degrees. Pressures become so intense that atomic nuclei slam together and fuse into heavier elements. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and so on, up the periodic table until you reach iron. Iron is where the process stops because fusing iron doesn't release energy, it actually requires energy input. When a massive star's core fills up with iron, the whole delicate balance that keeps the star shining suddenly collapses. Gravity takes over completely, crushing the core down to incredible density in less than a second. The core becomes so dense that protons and electrons get mashed together into neutrons. Then it bounces back, sending a shockwave racing outward through the star, blowing it apart in a supernova explosion. These explosions are among the most energetic events in the universe. For a brief time, a single dying star can shine brighter than the 100 billion stars in its host galaxy combined. The energy release is so enormous it's hard to find comparisons that make sense. If you could somehow harness the energy from one supernova, it would power human civilization at current energy usage rates for billions of years. What's left behind after these explosions depends on how massive the original star was. Stars that were 20 or 30 times more massive than our Sun leave behind black holes, regions of space where gravity is so strong that not even light can escape. Slightly smaller giants leave behind neutron stars, objects about the size of a city, but with more mass than our entire Sun, so dense that a teaspoon of neutron star material would weigh about 6 billion tons. This cycle of stellar birth, growth, and death is what makes the universe interesting. Without massive stars living and dying, there would be no heavy elements, no rocky planets, no complex chemistry, no life. The giants sacrifice themselves to make everything else possible. There's something almost generous about this process, the way these enormous stars give their substance to enrich the cosmos. Our Sun, ordinary as it seems, compared to these giants, has its own advantages. Because it's medium-sized, it burns its fuel slowly and steadily. It's been shining at roughly the same brightness for about 4.5 billion years, and it should keep doing so for another 5 billion or so. This stability is what makes life possible on Earth. The hypergiants are spectacular, but they're too chaotic, too short-lived to support the slow development of complex life. Size in the universe is always relative. These stellar giants seem impossibly large until you consider that they're just single points of light in galaxies containing hundreds of billions of stars. Galaxies themselves cluster together into larger structures, and those clusters form even larger groupings. The hierarchy of size keeps climbing upward, each level making the previous one seem small by comparison. When you try to imagine what it would be like to actually approach one of these hypergiant stars, the scale becomes even more overwhelming. The radiation would be intense beyond anything we experience near our Sun. Any planets that might have formed around such a star would either be stripped of their atmospheres or completely vaporized. These are not gentle, life-giving stars like our Sun. They're cosmic furnaces operating at the very limits of what physics allows. The light from these giants has often traveled for hundreds or thousands of years to reach us. When you look at Betelgeuse, you're seeing it as it was back when telescopes were first being invented. The star might have already exploded, and we just haven't seen the light from that explosion yet. This time delay adds another layer of mystery to these distant giants. Astronomers have discovered that many of these supergiant stars are variable, meaning their brightness changes over time. Some of this is because they're literally pulsating, expanding, and contracting like a slow heartbeat. Others change brightness because of complex processes in their atmospheres, massive storms or eruptions that can temporarily alter how much light they emit. The study of these giant stars has taught us about the life cycles of matter in the universe. Elements get created in stellar cores, scattered by supernova explosions, incorporated into new stars and planets, and eventually, some of those elements end up in living things. We are, quite literally, made of star stuff, the products of stellar alchemy that has been going on for billions of years. There's something humbling about contemplating these stellar giants. They remind us that our everyday experience of size and scale is just a tiny slice of what the universe contains. Objects so large they challenge our ability to visualize them. Processes so energetic they reshape entire regions of space, timescales that dwarf human history. All of this is happening constantly throughout the cosmos. These stars also represent a kind of cosmic democracy of elements. The heavy elements created in their cores don't stay locked away. They get distributed throughout space, becoming available to form the next generation of stars and planets. The universe has a way of recycling its contents, ensuring that the products of stellar evolution get shared widely. The universe builds its most magnificent structures not from single points of light, but from the scattered remains of stellar death and birth. Nebulae emerge when massive stars explode in their final moments, or when the raw materials of space slowly gather together. These cosmic formations represent something profound. They are simultaneously the nurseries where new stars begin, and the graveyards where old ones end their journey. Think about clouds drifting across an afternoon sky. Now imagine those clouds stretched not across kilometers, but across dozens, sometimes hundreds of light years. The word nebula literally means cloud in Latin, which seems almost quaint when you consider their true scale. These aren't wisps of water vapor, they're vast oceans of gas and dust floating in the emptiness between stars. The Orion Nebula sits right there in the constellation's sword, visible as just a faint smudge if you look up on a clear night. But that little blur spans about 24 light years from edge to edge. If you could somehow travel at light speed, the fastest anything can move in our universe, it would take nearly a quarter century just to cross from one side to the other. Our entire solar system, from the Sun out to the farthest planets, could fit inside that nebula thousands of times over. These cosmic clouds come in different varieties, each with its own personality. Some glow with their own internal light, powered by the radiation from nearby stars that excite their gas into brilliant displays. Others simply reflect starlight, like morning mist caught in a sunbeam, creating shimmering veils across space. Then there are the dark nebulae, so thick with dust that they block out the light from stars behind them, appearing as black patches against the starry background. The names can be misleading though. Planetary nebulae have absolutely nothing to do with planets. They're actually the outer layers of dying stars, puffed off into space, like cosmic smoke rings. These shells of glowing gas expand outward, growing larger and fainter as centuries pass. At their center sits what remains of the original star, often a white dwarf no bigger than Earth, but containing most of the original star's mass. Consider the Eagle Nebula, home to those famous pillars of creation that space telescopes have made into cosmic celebrities. Those towering columns look almost delicate in photographs, like wisps of smoke frozen in time. But each pillar stretches several light years tall, dwarfing not just our solar system, but entire collections of nearby stars. The apparent fragility is purely an illusion created by the vast distances involved. Inside these pillars, new stars are slowly forming, their growing light gradually eating away at the very clouds that gave them birth. It's a process that takes millions of years, but the outcome is inevitable. The stellar nursery eventually destroys itself through the success of its own creations. The Crab Nebula tells a more violent story. Nearly 1,000 years ago, Chinese astronomers noticed a new star that appeared bright enough to see in broad daylight. They called it a guest star, not knowing they were witnessing one of the most energetic events in the universe, a supernova explosion. That massive star tore itself apart with such force that we can still see the expanding debris cloud today. The Crab Nebula now spans about 11 light years across and continues growing outward at thousands of kilometers per second. At its heart spins a neutron star, the compressed core of the original giant, rotating 30 times each second and sweeping beams of radiation across space like a cosmic lighthouse. These stellar remnants connect us to something larger than just astronomical curiosity. The elements that make up our bodies, everything heavier than hydrogen and helium, were forged inside ancient stars and scattered into space when those stars died. Carbon, oxygen, nitrogen, iron, all the building blocks of life on Earth once drifted in nebular clouds, waiting to be gathered into new solar systems. We are quite literally made of star stuff, but more specifically, we're made of nebular material. Our origins stretch across light years of space and billions of years of time. Every atom in your body, except for hydrogen, was once part of these immense cosmic clouds. To get some sense of nebula scale, imagine shrinking our sun down to the size of a grain of sand. On that same scale, the Orion Nebula would cover an entire city. Its glowing clouds would fill neighborhoods, with tiny sand grains representing newly formed stars scattered throughout. Even with this dramatic reduction, the true size remains almost beyond comprehension. A single light year equals nearly 10 trillion kilometers. When astronomers describe nebulae as 20 or 100 light years across, they're talking about distances so vast that human minds can barely label them, let alone truly grasp their meaning. We can work with the numbers, but the reality exceeds our capacity for genuine understanding. Despite their enormous size, nebulae are surprisingly fragile structures. The very stars they create eventually destroy them through ultraviolet radiation and stellar winds that blast their material back into space. Over millions of years, these cosmic clouds disperse, their gas either consumed by star formation or scattered into the interstellar medium. This creates a beautiful irony. The largest, most spectacular structures in our local universe are also temporary. They exist for cosmically brief moments, creating new generations of stars before fading away. Their immensity is real but fleeting, like vast flowers that bloom and scatter. On timescales measured in geological ages, the colorful images we see from space telescopes can be misleading in their own way. Those brilliant reds and blues often represent invisible wavelengths of light, mapped to colors our eyes can perceive. If you could somehow float inside a nebula, you might see only dim, subtle glows, like stars shining through thin veils of mist, but the scale would be undeniable. You could travel for multiple human lifetimes in any direction and never leave the cloud. The space around you wouldn't be empty. It would be filled with molecules and dust grains and individual atoms, all drifting through a volume larger than anything on Earth by countless orders of magnitude. Nebulae reveal something important about how the universe organizes itself. Stars don't form randomly, scattered like seeds thrown across a field. They're born in clusters, in bursts of creation, within these vast molecular clouds. A single nebula can produce thousands of new stars, each potentially surrounded by its own family of planets. The Orion Nebula alone contains about 2,000 young stars within just a few dozen light years. Each one could host planetary systems. Each one represents the possibility of worlds, perhaps even life, developing around distant suns. That faint smudge, visible to your naked eye, contains more potential futures than we could ever count or imagine. Yet, even these immense structures are building blocks for something larger still. Nebulae feed into galaxies, becoming part of even grander collections that span tens of thousands of light years. Their impressive scale prepares us to consider the next level of cosmic architecture, where individual clouds and stars give way to vast spiral arms and galactic communities containing hundreds of billions of suns. When you step outside on a clear night, your eyes naturally search for patterns in the darkness above. Some of those tiny points of light, scattered across the vast canvas of space, aren't actually scattered at all. They're families, bound together by invisible threads of gravity, moving through the cosmos as one. These stellar families come in different shapes and sizes, each telling its own story about the universe we inhabit. The smaller gatherings, called open clusters, are like loosely knit communities of young stars. Picture a neighborhood where everyone was born around the same time, where the houses are spread out but still connected by shared history. Open clusters typically hold a few hundred, maybe a few thousand stars, all drifting together across regions of space that span dozens of light years. These stellar neighborhoods don't last forever though. Over hundreds of millions of years, the stars slowly drift apart, like childhood friends who eventually move to different cities. But then there are the globular clusters. And these are something entirely different. If open clusters are neighborhoods, globular clusters are ancient cities, packed with hundreds of thousands, sometimes millions of stars, all crowded into a relatively small cosmic space. The famous Pleiades cluster, visible to the naked eye as a small group of bright stars, contains more than 1,000 suns. These stars were all born together, roughly 100 million years ago, which makes them quite young by cosmic standards. They're hot, blue and brilliant, still wrapped in wisps of the gas cloud that gave them birth. From our perspective on Earth, they appear close together, like diamonds scattered on black velvet. But the reality is staggering. These stars span about 43 light-years of space, each one separated from its neighbors by distances so vast that light itself takes years to cross the gaps between them. Yet they remain bound together, a testament to the strange mathematics of gravity that can hold entire families of stars in cosmic embrace. There's something almost poetic about this. The way these massive nuclear furnaces, each one capable of warming entire solar systems, choose to travel together through the darkness. The globular clusters take this concept to an almost incomprehensible extreme. Consider Omega Centauri, the largest such cluster in our galaxy. It contains an estimated 10 million stars, all packed into a sphere roughly 150 light-years across. From Earth, even without a telescope, it appears as nothing more than a fuzzy patch of light, but through a powerful telescope, it transforms into something magnificent, a dazzling swarm of stars packed so tightly that if you could somehow visit a planet inside such a cluster, your night sky would be ablaze with hundreds of bright suns. Each one would shine as brightly as our moon appears to us. Darkness, as we know and understand it, would essentially cease to exist. The sky would be a glowing sea of light in every direction, overwhelming in its intensity, beautiful beyond imagination. These globular clusters are ancient beyond our everyday comprehension. Many formed more than 12 billion years ago, when the universe itself was young, only a fraction of its current age. The stars within them are old, faint, and red, long past their youthful brilliance. In many ways, these clusters serve as cosmic fossils, living archives of an earlier era in the universe's history. Their immensity isn't just measured in the number of stars they contain, but in their age, their persistence, their remarkable ability to endure across vast stretches of cosmic time. The process by which these stellar families form reveals something profound about the nature of space itself. Stars are rarely born alone. Instead, they emerge from collapsing clouds of gas and dust that fragment into multiple motes, each one eventually becoming a star. These newborn stars share momentum, orbiting around a common center of mass, bound together by the same gravitational forces that created them. Some eventually wander away, becoming cosmic nomads, while others remain forever tied to their stellar siblings. It's worth remembering that these clusters, despite their apparent permanence, are not static fixtures in the sky. Open clusters gradually drift apart, their member stars eventually becoming indistinguishable from the background population of our galaxy. Even the mighty globular clusters slowly erode over time, as gravitational tides from the galaxy itself gradually pull them apart. But for millions, sometimes billions of years, they remain coherent, traveling together as families of suns through the cosmic wilderness. When we look at a star cluster from Earth, we're witnessing something that fundamentally challenges our perception of scale. Instead of seeing stars scattered randomly across thousands of light-years of space, we see them organized into recognizable patterns, grouped together in ways that speak to the hidden architecture of the cosmos. The universe, it turns out, is not a random collection of objects scattered through emptiness. It's structured, organized, layered in ways that reveal themselves only when we learn to look with the right eyes, to think on the right scales. Consider again those Pleiades, those 7 sisters of mythology. Each individual star in that cluster is massive compared to our sun, many times brighter, many times larger, yet together they appear as delicate jewels sprinkled across our night sky, close enough to seem intimate familiar. Our eyes cannot measure the true distances involved. Our minds must do the work of translation, helping us understand that each star is separated from its neighbors by light years, by vast gulfs of apparently empty space, and yet they belong together, moving as a unified group along a path through our galaxy that will persist for millions of years to come. For astronomers, star clusters serve as natural laboratories for understanding how stars work. Because all the stars in a given cluster formed at roughly the same time, from the same raw materials, any differences between them can be attributed to differences in mass, rather than age or chemical composition. This makes clusters invaluable tools for studying stellar evolution, for understanding the life cycles of stars, how they're born, how they live, and ultimately how they die. In this sense, their significance extends beyond the merely physical into the realm of knowledge itself. They are vast not only in their numbers and distances, but in their meaning, in the insights they offer into the fundamental processes that shape our entire cosmos. Yet, like every scale we encounter in our exploration of the universe, star clusters themselves are not the ultimate expression of cosmic magnitude. They are stepping stones, way stations on a journey toward even grander scales of organization. These swarms of stars, as impressive as they are, remain only fragments of something larger, components in an even more magnificent cosmic architecture. Our own Milky Way galaxy contains more than 150 known globular clusters, each one immense in its own right, yet each one merely a satellite, a small companion to something incomparably greater. The scale of star clusters prepares our minds for the next leap, toward galaxies themselves, where billions upon billions of stars gather into vast disks and spirals, each one larger than everything we've considered up to this point. Looking up at the night sky, we see what appears to be countless individual points of light scattered across darkness. But there's something profound happening here that our eyes can't quite grasp. Every single star we can see belongs to one massive structure, our home galaxy, the Milky Way. It's like standing inside a vast city and being unable to see the city itself, only the individual buildings around us. The Milky Way stretches about 100,000 light-years from edge to edge. That distance is almost impossible to feel in any meaningful way. If you could somehow travel at light speed, the fastest thing in the universe, it would still take you 100,000 years to cross from one side to the other. And within this enormous spiral structure, there are somewhere between 100 billion and 400 billion stars, each one potentially hosting planets, moons, asteroid belts, all the cosmic debris that comes with stellar systems. If you decided to count these stars, one per second without stopping to sleep or eat, you'd be counting for more than 10,000 years just to reach the lower estimate. The human mind struggles with numbers this large. They become abstract, almost meaningless in their vastness. Yet each of those numbers represents an actual burning star, a nuclear furnace that might warm worlds we'll never know about. What's even more staggering is that our galaxy, with all its hundreds of billions of stars, is just one among countless others. When early astronomers first realized this, it completely transformed how we think about our place in the cosmos. For a long time, many scientists believed the Milky Way was everything, the entire universe. Then they discovered that what looked like fuzzy patches of light were actually other galaxies, separate island universes, as they were poetically called. The Andromeda Galaxy sits about 2.5 million light-years away from us. It's even larger than the Milky Way, containing over 1 trillion stars. Through a telescope, you can see it as a faint smudge, but that smudge spans more than 200,000 light-years. Somewhere in that distant spiral, there might be beings looking back toward us, wondering about the faint patch of light that is our galaxy. There's something almost philosophical about this mutual observation. Two island universes, each filled with billions of opportunities for complexity, for life, for consciousness, gazing across the void at each other. The scale creates a kind of cosmic loneliness, but also a sense of infinite possibility. Every star could be a sun to someone, every galaxy a home to countless stories we'll never hear. Galaxies come in different varieties, like cosmic architecture taking on various forms. Spiral galaxies like ours have these beautiful sweeping arms that curve outward from a central bulge. At the very center, there's usually a supermassive black hole, an object so dense that not even light can escape its gravitational pull. These black holes can contain the mass of millions or even billions of stars, compressed into a space smaller than our solar system. Elliptical galaxies look quite different. They're more like vast, featureless footballs in space, containing hundreds of billions of older stars. Many have used up most of their gas, so they're not forming new stars anymore. They're like cosmic retirement homes, filled with ancient suns slowly burning through their remaining fuel. Then there are irregular galaxies, chaotic and asymmetrical, often twisted into strange shapes by gravitational interactions with their neighbors. These show us that galaxies aren't static monuments in space. They're dynamic, living structures that change and evolve over billions of years. Our own Milky Way and Andromeda are actually on a collision course. In about 4 billion years, they'll merge into a single, larger galaxy. Despite the dramatic language, this cosmic collision will be surprisingly gentle. The stars are so far apart that most won't actually hit each other. Instead, the two galaxies will pass through each other like ghosts, their shapes slowly distorting, their stars thrown into new orbits around the combined center. This kind of galactic cannibalism happens regularly throughout the universe. It's how galaxies grow larger, consuming their smaller neighbors, combining their stars and gas clouds. The process creates bursts of new star formation as gas clouds collide and compress. Over cosmic time, the merged galaxies settle into new configurations, usually elliptical in shape. Some galaxies have grown to truly mind-boggling sizes through these mergers. There's one called IC 1101, an elliptical galaxy that stretches more than 6 million light-years across. It contains perhaps 100 trillion stars. That number is so large it loses all meaning, becomes just a collection of syllables. 100 trillion individual nuclear furnaces, each potentially warming planets, all gravitationally bound into a single structure. The scale of galaxies reveals something interesting about the universe's architecture. At their centers, these massive structures are often organized around supermassive black holes, objects that represent the ultimate compression of matter. The largest structures in the universe, containing hundreds of billions of stars, are held together by some of the smallest, densest objects imaginable. There's a beautiful paradox in this. The way cosmic enormity depends on cosmic compactness. When we try to visualize galaxies, it helps to think of them as cities. Each star is like a house, each star cluster like a neighborhood, each spiral arm like a great avenue stretching across light years. The dark lanes of cosmic dust are like rivers or forests between districts, shaping where the brightest stars can form. The analogy isn't perfect, but it captures something about the organized complexity of these structures. Just as cities contain countless individual lives and stories, galaxies contain countless stars, each with its own potential for planets, for chemistry, for the complex interactions that might lead to life. The scale of a galaxy isn't just about distance or light years. It's about multiplicity, about the sheer number of possibilities contained within a single gravitational system. From Earth, we can only see a few galaxies with our naked eyes. The Milky Way itself appears as that pale band of light stretching across dark skies, our inside view of our own galaxy's disk. Under very dark conditions, you can spot Andromeda as a faint fuzzy patch, and from the southern hemisphere, the Large and Small Magellanic Clouds, two smaller galaxies that orbit around ours. But telescopes reveal the true abundance. The famous Hubble Deep Field image was created by pointing the Hubble Space Telescope at a tiny patch of seemingly empty sky, about the size of a grain of sand held at arm's length. That tiny region contained thousands of galaxies, each one home to billions of stars. When you extrapolate that across the entire observable sky, astronomers estimate there are hundreds of billions of galaxies in the visible universe. Each one of those galaxies represents a complete cosmic ecosystem, a gravitationally bound city of stars stretching across tens or hundreds of thousands of light years. Each one contains more stars than there are people who have ever lived on Earth. And each one is just a single point of light in the larger cosmic web, part of galaxy clusters and superclusters that organize matter on even larger scales. The immensity becomes recursive, almost fractal, in its endlessness. Just when you think you've grasped the scale of a galaxy, you realize that galaxies themselves are just building blocks in larger structures. Galaxy clusters contain thousands of galaxies. Superclusters contain thousands of galaxy clusters. And these structures form filaments and walls that stretch across hundreds of millions of light years, creating a cosmic web that spans the observable universe. We live inside this hierarchy of scale, embedded in structures so vast that we can barely conceptualize them. Yet we're also made of atoms that once formed inside distant stars, part of the cosmic recycling that has been operating for billions of years. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was forged in stellar furnaces scattered throughout our galaxy. In a way, we're not just observers of galactic scale, we're participants in it. We're made of galactic material, shaped by galactic processes, part of the ongoing story of how matter organizes itself into ever more complex structures. The immensity that seems so alien and distant is also, in the most fundamental sense, the story of where we came from and what we're made of. The Milky Way stretches across 100,000 light-years of space, maybe even more, according to some measurements. When you really think about it, that distance becomes almost meaningless to us. Our minds just can't grasp numbers that large. But here we are, floating inside this enormous spiral, looking out at it from the inside like passengers on a cosmic ship. We can never step off. Somewhere between 100 billion and 400 billion stars call this galaxy home. That range alone tells you how difficult it is to count something so vast. Each of those stars might have planets, and around those planets, who knows what stories are unfolding right now. The whole structure spins slowly through space, carrying us along whether we think about it or not. Our sun sits about 27,000 light-years from the center, tucked away in what astronomers call the Orion Spur. It's like living in the suburbs of the galaxy, far enough from downtown to avoid the chaos, but not so far out that you're completely isolated. This location probably saved our planet from all sorts of cosmic disasters over the billions of years life was trying to get started here. The galaxy's center holds a monster, a black hole called Sagittarius A star. It weighs about 4 million times as much as our sun, but you'd never see it directly. Black holes don't give off light, they swallow it. We only know it's there because of how everything else behaves around it. Stars whip around this invisible anchor at incredible speeds, like moths circling a flame they can never touch. Think about this for a moment. The entire galaxy, with all its hundreds of billions of stars, revolves around something you can't even see. It's a reminder that the most powerful forces in the universe often work in silence, shaping everything while remaining hidden from view. Our whole solar system takes somewhere between 225 and 250 million years to complete one orbit around this galactic center. Since Earth formed, we've made this journey more than a dozen times. But human civilization, all of recorded history, everything we consider ancient, has happened during just a tiny fraction of one of these cosmic years. When you look up at the night sky on a clear evening, that pale band of light stretching across the darkness, that's your view of the Milky Way from the inside. You're looking along the flat disk of the galaxy, peering through thousands of light-years of stars, all compressed into what looks like a soft, glowing river. The galaxy isn't uniform, though. Some regions blaze with young, hot blue stars that burn bright and die fast. Other areas contain older, dimmer populations that have been quietly shining for billions of years. Between the spiral arms, vast clouds of hydrogen drift through space, waiting to collapse and form the next generation of stars. Most of what makes up our galaxy, you can't see at all. Dark matter outweighs everything visible by a huge margin. Without this invisible scaffolding holding things together, the galaxy would simply fly apart. Its rotation would fling stars into the void instead of keeping them in those graceful spiral patterns. The space between stars is almost incomprehensibly empty. If you shrunk the sun down to the size of a ping-pong ball, the nearest star would be another ping-pong ball placed over 1,000 kilometers away. Galaxies look solid in photographs, but they're mostly nothing at all, just vast amounts of emptiness, punctuated by tiny points of light. This emptiness isn't really empty, though. It's filled with possibilities, with radiation, with magnetic fields, with the remnants of ancient explosions. Space has texture and character, even where there's nothing obvious to see. The Milky Way doesn't travel alone through the cosmos. Two smaller galaxies called the Large and Small Magellanic Clouds orbit around us like cosmic pets. They're being slowly torn apart by our galaxy's gravity, leaving trails of gas that stretch across millions of light years. Even galaxies can be bullies sometimes. We're part of what's called The local group, a collection of more than 50 galaxies, all bound together by gravity. The biggest member after us is Andromeda, a spiral galaxy even larger than our own. In about 4 billion years, these two galaxies will collide and merge, creating something entirely new. The night sky of that distant future will look nothing like what we see today. Ancient peoples looked up at the Milky Way and saw a river of milk spilled across heaven, or a path that souls traveled after death. They gave it names that reflected wonder and mystery. Today, light pollution hides this cosmic river from most of us. We've gained knowledge about what it really is, but lost the daily reminder of our place in something immeasurably vast. The scale becomes more manageable if you imagine shrinking the entire galaxy down to the size of North America. On that scale, our solar system would be smaller than a coin. Everything humans have ever experienced, every war and love story and scientific discovery, would fit inside that tiny circle while the galaxy stretches from ocean to ocean around it. This perspective shift does something interesting to your sense of importance. Are we insignificant specks in an indifferent universe? Or are we remarkable accidents? The only place we know of where the cosmos has become aware of itself. Maybe the question itself is more important than any answer we might find. Stars are being born and dying in the Milky Way right now, as you listen to this. Gas clouds are collapsing under their own weight, reaching temperatures and pressures that ignite nuclear fusion. Massive stars are exploding, as supernovae, scattering heavy elements through space, the same elements that make up your body. The galaxy is not a static photograph, it's a living, changing system. Over billions of years, the galaxy has evolved. Star formation rates have changed. The spiral arms have wound and unwound. Smaller galaxies have been absorbed, adding their stars to our collection. The Milky Way you see tonight is different from the one that existed when the first life forms appeared on Earth, and it will keep changing. Eventually, that collision with Andromeda will transform both galaxies into something new, probably a giant elliptical galaxy with a completely different character. The name Milky Way might not even apply anymore. Nothing lasts forever, not even structures this immense. When we try to comprehend the galaxy, we inevitably fall back on metaphors and comparisons because our brains simply aren't equipped to process these scales directly. We talk about cosmic cities and rivers of stars and neighborhoods of space. These aren't perfect descriptions, but they're the best tools we have for making the incomprehensible slightly more familiar. Perhaps that's part of what makes science so human. We take measurements and gather data, but in the end, we still need stories to make sense of what we've discovered. The universe doesn't care whether we understand it or not, but we keep trying anyway, driven by something deeper than mere curiosity. The Milky Way represents home on the largest possible scale, but it also points beyond itself. Just as planets orbit stars and stars belong to galaxies, galaxies cluster together into even larger structures. Our cosmic neighborhood extends outward through groups and clusters and superclusters, each level revealing new patterns and connections. Standing on Earth, looking up at that faint band of light, you're seeing your cosmic address from the inside. You're part of something so large that light takes 100,000 years to cross from edge to edge. And yet, somehow, it's all connected, all part of one vast, slowly turning wheel of stars and darkness, carrying you through space and time on a journey that started long before you existed and will continue long after you're gone. Imagine islands of 100 billion stars, each one drifting through the cosmic dark. These vast collections, what we call galaxies, aren't sitting still like portraits frozen in time. They're moving, constantly, pulled by invisible threads of gravity that stretch across unimaginable distances. Every galaxy has neighbors. Some close, some far, but all connected by the same force that keeps your feet on the ground. Over millions of years, these massive star cities travel along paths that sometimes inevitably cross. When they do, something remarkable happens. Two galaxies begin what might be the universe's slowest dance. The word collision makes it sound violent, like car crashes or asteroid impacts. But galactic meetings are nothing like that. Picture two clouds of fireflies drifting toward each other. The fireflies almost never touch. There's just too much empty space between them. But the clouds themselves, their shapes, their boundaries, those blend and merge and transform. This is what happens when galaxies meet. They're stars separated by distances so vast that light takes years to cross them, rarely collide directly. Instead, the galaxies pass through each other like ghosts. Their gravitational fields tangle together. Their gas clouds compress and spark. Their spiral arms stretch into long, graceful streamers that can span hundreds of thousands of light years. The timescales involved stretch our understanding of duration itself. From the first gravitational tug to the final merged form can take billions of years. That's longer than life has existed on Earth. Longer than the Earth itself has existed. No conscious being could ever witness the complete story, from beginning to end. We see these cosmic encounters frozen in our telescopes, single moments captured from stories that began when the universe was young. The antenna galaxies, hanging in space about 45 million light-years away, show us this process in action. Two spiral galaxies, once separate and distinct, now stretching into long arcs that really do look like insect antennae, reaching across the void. Where their gas clouds meet and compress, something beautiful happens. New stars ignite by the thousands. The collision isn't destroying these galaxies, it's creating within them. Stellar nurseries burst into life, new suns form, and with them, potentially, new worlds. Our own galaxy, the Milky Way, isn't immune to this cosmic choreography. Right now, as you listen to this, we're approaching our nearest large neighbor, the Andromeda Galaxy. The two of us are racing toward each other at about 110 kilometers per second. That sounds terrifyingly fast until you remember the distances involved. We're still 2.5 million light-years apart. At our current speed, we won't meet for another 4 billion years. When we do, the night sky will transform completely. Andromeda will grow larger and larger over millions of generations. Until the two galaxies embrace, the merger will create a new kind of galaxy entirely. Some astronomers have playfully named this future giant Milkomeda, or Milkdromeda. It will be larger than either of its parents, a massive elliptical galaxy born from the union of two spirals. For any life that might exist then, the changes would be profound but gradual. Stars might be flung into new orbits, some might be ejected entirely, cast out to wander the spaces between galaxies. Others might find themselves in completely different neighborhoods, surrounded by unfamiliar constellations. But this wouldn't happen overnight in any sense we understand. The transformation would unfold across timescales that dwarf the entire history of complex life. Each generation of living beings would see essentially the same sky, even as the grand restructuring continued around them. The Whirlpool Galaxy offers us another glimpse of this process. A large spiral is slowly devouring a smaller companion. The gravitational interaction has triggered waves of star formation that light up the spiral arms like a cosmic pinwheel. The smaller galaxy is being stretched and distorted, its material gradually incorporated into its larger partner. These encounters can feed the supermassive black holes that lurk at galactic centers. As gas and dust spiral inward, compressed by the collision, some of it falls into these gravitational monsters. The black holes flare to life as quasars, among the brightest objects in the universe, visible across billions of light years. Our own galaxy bears the scars and signatures of past collisions. Streams of stars wrap around the Milky Way like ribbons, the remains of smaller galaxies we've consumed over billions of years. The Sagittarius dwarf galaxy is being torn apart right now, its stars scattered into long trails that astronomers can map and study. This is how galaxies grow, how they evolve, how they become the massive structures we see today. The smooth, round shapes of giant elliptical galaxies are thought to be the end result of multiple spiral galaxy mergers. Each one represents countless ancient encounters, a fossil record written in stars and gas What's remarkable is how these vast, slow catastrophes create such intricate beauty. Telescope images of colliding galaxies look almost artistic, delicate streams of light curved through darkness, spiral arms twisted into elegant shapes, bright knots where new stars are being born. The scale challenges our ability to truly comprehend it. We can say billions of stars, millions of light years, billions of years, but these numbers slip into abstraction. They're too large for the human mind to fully grasp. Yet when we see the results, there's something immediately recognizable about the patterns, something that speaks to our sense of form and beauty. Perhaps this is because the same fundamental forces that shape galactic collisions operate everywhere in the universe. Gravity, momentum, conservation of energy, these aren't special cosmic laws. They're the same rules that govern water swirling down a drain, or leaves caught in the wind. The difference is one of scale and time. What takes seconds in our everyday experience unfolds over eons in space. What affects individual particles on Earth shapes the destiny of entire star systems in the cosmos. Even these galactic encounters, vast as they are, represent just one level of cosmic organization. Galaxies themselves cluster together in groups and larger clusters, dozens or hundreds of them bound by gravity across millions of light years. Within these clusters, collisions and interactions are common, a constant reshaping of cosmic neighborhoods. The immensity here isn't just about size or mass or distance, it's about connection, about the way seemingly separate objects influence each other across space and time. No galaxy is truly alone. Each one participates in a web of gravitational relationships that extends throughout the observable universe. This connectivity offers a different way of thinking about largeness, about what it means for something to be immense. A galaxy's true size includes not just its stars and gas and dark matter, but its history, its future transformations, its role in the broader cosmic story. When we look up at the night sky, we're seeing participants in this grand network, islands of stars that are simultaneously individuals and parts of something larger. Their dance continues around us, too slow for us to perceive directly, but reshaping the universe with every graceful step. Galaxies huddle together like cities gathering into vast metropolitan regions. These cosmic neighborhoods, called galaxy clusters, stretch our understanding of space beyond what any human mind was meant to grasp. When you picture a galaxy cluster, imagine thousands of entire galaxies, each containing billions of stars, all bound together by the invisible hand of gravity across distances so enormous that light itself takes millions of years to make the journey from one side to the other. The numbers alone make your head spin. A single cluster might contain 1,000 galaxies, maybe more. Each of those galaxies holds roughly 100 billion stars. That means we're looking at numbers with so many zeros that even astronomers prefer to speak in shorthand. It's like trying to count every grain of sand on every beach on Earth, then multiplying that by 1,000,000. Our own galaxy, the Milky Way, lives in what scientists call the local group. It's a modest neighborhood by cosmic standards, home to just over 50 galaxies, including our neighbor Andromeda. But compared to the truly massive clusters out there, the local group is more like a small town than a bustling metropolis. The Virgo cluster, sitting about 65 million light-years away, contains over 1,000 galaxies packed into a space so vast that our entire local group would fit inside it like a single room in a mansion. What's fascinating is how these galactic cities stay together at all. The space between galaxies within a cluster is mostly empty, yet something keeps them from drifting apart into the cosmic void. That something is dark matter, the mysterious substance that makes up most of the universe but refuses to interact with light in any way we can detect directly. Dark matter outweighs all the visible matter in a cluster by enormous margins. Without its gravitational embrace, these cosmic neighborhoods would simply dissolve, their galaxies wandering off alone into the darkness. Between the galaxies in a cluster lies something unexpected, a thin soup of gas, heated to temperatures that would make the core of the sun seem chilly by comparison. This gas reaches tens of millions of degrees, so hot it glows with X-ray light invisible to human eyes but detectable by specialized telescopes. The gas is incredibly thin, thinner than the best vacuum we can create in laboratories on Earth. Yet when spread across the immensity of a cluster, it adds up to more mass than all the galaxies combined. Think about that for a moment. The empty space isn't really empty at all. It's filled with this ghostly medium, a cosmic atmosphere that connects one galaxy to another across millions of light years. In some ways, a galaxy cluster resembles a living organism more than a simple collection of objects, with this hot gas serving as a kind of circulatory system that binds everything to these cosmic scales. The Coma cluster offers another glimpse into these cosmic scales. Located about 330 million light-years from Earth, it swarms with thousands of galaxies. When astronomers photograph it, the image looks almost like a busy highway at night, each point of light representing not a car, or even a city, but an entire galaxy containing billions upon billions of stars. It's as if someone took our night sky and replaced every star with a complete galaxy, then multiplied that scene 1,000-fold. These clusters aren't static museums pieces either. They're dynamic, ever-changing communities where galaxies dance around each other, under the influence of mutual gravity. Collisions happen regularly on these scales, though they unfold over hundreds of millions of years. When galaxies merge, they trigger bursts of star formation, reshape their spiral arms, and sometimes create entirely new types of galactic structures. It's urban renewal on a cosmic scale, with neighborhoods constantly being rebuilt and reimagined. The gravity of these massive clusters does something remarkable to the fabric of space itself. Einstein showed us that gravity bends space and time, and nowhere is this more apparent than around galaxy clusters. The immense gravitational field acts like a cosmic magnifying glass, bending and distorting light from even more distant galaxies behind the cluster. Astronomers call this gravitational lensing, and it turns these cosmic neighborhoods into natural telescopes that help us peer deeper into space than we could otherwise manage. By studying these distorted images, scientists can map the invisible dark matter within clusters, watching how it clumps and flows in ways that ordinary matter cannot. It's like being able to see the wind by watching how it moves the leaves. Except here, we're watching how invisible matter moves entire galaxies. Time plays its own role in this cosmic drama. Galaxy clusters don't spring into existence, fully formed. They grow slowly over billions of years as smaller groups of galaxies find each other and merge under their mutual gravitational attraction. Some clusters we observe today are still in the process of formation, their member galaxies still falling toward the center, their hot gas still settling into equilibrium. The largest clusters can stretch 10 million light-years across, distances so vast that even our entire galaxy becomes just a tiny detail in the overall structure. It's humbling to realize that Earth, the solar system, even the Milky Way itself all disappear into insignificance when viewed from the perspective of a galaxy cluster. We're not just small, we're layers within layers of smallness, like Russian nesting dolls that keep getting tinier as you work your way down. But perhaps the most mind-bending aspect of galaxy clusters is that they're not the end of the story. These immense structures, already beyond our ability to truly comprehend, gather together into even larger groupings called superclusters. Our local group, modest as it is, belongs to the Virgo supercluster, which itself is part of an even grander structure. Astronomers have named Laniakea. The scale keeps expanding outward, reminding us that no matter how far we zoom out, there's always something bigger waiting to surprise us. These cosmic neighborhoods force us to reconsider what we mean by large, by significant, by important. They remind us that the universe operates on scales that dwarf not just our physical existence, but our very capacity for imagination. Yet somehow, from our tiny vantage point on a small planet orbiting an ordinary star in an unremarkable galaxy, we've managed to discover and begin to understand these magnificent structures. Perhaps that's the most remarkable thing of all. Looking out into the night sky, we see stars scattered like distant streetlights. But these points of light belong to something much grander than we might first imagine. Every star we can see with our naked eyes lives inside our own galaxy, the Milky Way, which contains somewhere around 100 billion other stars, all held together in a slow cosmic dance by gravity's patient pull. But here's where things get interesting. Our galaxy isn't alone out there. It has neighbors, other massive collections of stars spinning through the darkness. The Milky Way belongs to what astronomers call the local group, a small gathering of about 80 galaxies all bound together by their mutual gravitational attraction. It's like a cosmic neighborhood, where our galaxy and the Andromeda Galaxy are the two largest houses on the block. Now, if you think that sounds big, well, we're just getting started. The local group itself is part of something even larger, something called the Virgo cluster. Picture this: thousands of galaxies, each one containing billions of stars, all orbiting around their common center of gravity. The scale starts to feel almost incomprehensible when you realize that each galaxy is already an island universe in its own right. But the universe has an even grander architecture waiting for us. These galaxy clusters don't just float around randomly in space. They connect to each other, forming massive structures called superclusters. These are like the highways of the cosmos, connecting different neighborhoods of galaxies across distances that stretch the imagination. Our local group, sitting inside the Virgo cluster, belongs to something called the Virgo supercluster. This structure spans about 110 million light-years from end to end. To put that in perspective, light, traveling at the fastest speed possible in our universe, would take 110 million years to cross from one side to the other. Entire civilizations could rise and fall in the time it takes a single photon to make that journey. The story doesn't end there, though. Recent discoveries have shown us that even our home supercluster is just a piece of something larger. Scientists have identified an even more massive structure called Laniakea, which means immense heaven in Hawaiian. This cosmic giant contains about 100,000 galaxies and stretches across more than 500 million light-years. Think about that for a moment. Every star you've ever seen, every galaxy we've photographed with our most powerful telescopes, every cosmic wonder that has inspired humanity to look up and dream, all of it sits within this one supercluster. It's humbling in a way that makes our daily concerns feel both insignificant and precious at the same time. When astronomers map these superclusters, something remarkable emerges. The universe doesn't look random at all. Instead, it resembles a vast spiderweb, with long filaments of galaxies stretching across cosmic voids. These threads of light connect dense nodes, where galaxy clusters gather, creating a pattern that looks surprisingly like the foam on top of your morning coffee. If that foam were made of stars and stretched across billions of light-years. The empty spaces between these cosmic threads are called voids, and they're almost incomprehensibly empty. Imagine flying through one of these voids in a spaceship. You could travel for millions of years at the speed of light and encounter hardly any galaxies at all. The loneliness would be absolute, the darkness profound, broken only by the distant glow of galactic filaments marking the edges of your cosmic desert. Projects like the Sloan Digital Sky Survey have mapped these structures in incredible detail, revealing patterns that stretch across enormous distances. The Sloan Great Wall, for instance, spans about 1.4 billion light-years. To call it a wall might be misleading, though. It's more like a sheet of galaxies, a cosmic membrane dividing vast regions of nearly empty space. These aren't really objects in the way we normally think about things. You can't point to a supercluster and say, there it is, the way you might point to a mountain or even a star. Instead, they're patterns, relationships between countless galaxies, all influenced by gravity's gentle but persistent tug across unimaginable distances. The architecture of these structures tells us something profound about how the universe works. Gravity acts like a cosmic sculptor, pulling matter together into increasingly complex hierarchies. Stars form galaxies, galaxies form clusters, clusters form superclusters, and superclusters connect into this grand cosmic web that fills all of observable space. But here's something that might keep you awake at night, in the best possible way. These structures aren't frozen in time. They're constantly evolving, growing, changing as the universe expands around them. Galaxies slide along these cosmic filaments like cars on a highway, gradually clustering together in denser regions while the empty voids grow larger and more empty. The expansion of space itself adds another layer of complexity to this story. While gravity pulls matter together locally, the expansion of the universe stretches the distances between these massive structures. It's like watching a slow-motion explosion where some pieces stick together while others drift apart, creating an ever-changing tapestry of matter and emptiness. This raises fascinating questions about what might exist beyond what we can see. Are there even larger structures out there, connecting superclusters into something we haven't discovered yet? Some scientists think there might be, but we're approaching the limits of what's observable from our cosmic vantage point. The expansion of the universe itself creates a horizon beyond which we simply cannot see. Light from the most distant structures hasn't had time to reach us yet, and some regions are moving away so fast that their light may never arrive. In a sense, the universe keeps its biggest secrets hidden behind this cosmic curtain. When you try to imagine the true scale of a supercluster, metaphors start to break down. If you shrunk our entire galaxy down to the size of a grain of sand, the Virgo supercluster would still stretch for hundreds of kilometers. Every grain of sand in that vast web would contain billions of stars, each one potentially hosting worlds we'll never know about. The immensity isn't just in the things themselves, but in the spaces between them. The cosmic web is as much about emptiness as it is about matter, vast gulfs of nearly nothing stretching between islands of light and energy. It's a universe of contrasts, where the densest galaxy clusters exist alongside voids so empty that entire civilizations could exist without ever knowing that other galaxies exist at all. From our perspective here on Earth, looking up at the night sky, these superclusters represent layers of belonging that extend outward like nested dolls. We live on a planet, orbiting a star, in a galaxy that's part of a group, in a cluster, within a supercluster, connected to a web that fills the observable universe. Each layer dwarfs the one before it, stretching our sense of scale until words like big and far lose their everyday meaning. Perhaps what's most remarkable about these cosmic webs is how they remind us that everything in the universe is connected. The same gravity that keeps your feet on the ground also shapes the largest structures we know. The atoms in your body were forged in stars that belong to this vast cosmic architecture, making you not just an observer of these immense structures, but quite literally a part of them. And yet, even these superclusters, vast as they are, represent just one more step on a ladder that seems to have no end. Beyond them lies the entire observable universe, stretching nearly 93 billion light-years from edge to edge, filled with cosmic webs that connect everything to everything else in patterns we're only beginning to understand. The universe reveals its secrets slowly, and when scientists first started creating three-dimensional maps of space, what they discovered changed everything we thought we knew about cosmic architecture. Instead of finding galaxies scattered randomly like dust in the wind, they uncovered something far more extraordinary, a vast network that stretches across unimaginable distances. This network, known as the cosmic web, represents the largest known structure in existence. Picture highways of galaxies, stretching for hundreds of millions of light-years, connecting at massive intersections where thousands of galaxy clusters gather like cosmic cities. Between these luminous threads lie enormous empty regions, voids so vast they contain almost nothing at all. The resemblance to familiar patterns is striking, almost unsettling. The cosmic web looks remarkably similar to neural networks in our brains, or the delicate strands of a spider's web glistening with morning dew. There's something profound about finding these echoes, the same organizational principles, appearing at the smallest and largest scales we can observe. When we talk about the size of these filaments, words begin to lose their meaning. A single strand can span 500 million light-years, containing hundreds of thousands of galaxies. Each galaxy holds billions of stars, each star potentially warming its own family of planets. The light traveling from one end of such a filament to the other takes 500 million years to complete its journey. Think about that for a moment. When dinosaurs first walked the Earth, photons were just beginning their journey from distant galaxies, and they're only reaching our telescopes now. Time and space become intertwined at these scales, creating a tapestry where distance is measured in errors, not miles. Among the largest known structures sits the Hercules Corona Borealis Great Wall, a supercluster complex stretching roughly 10 billion light-years across. The light we see from this structure has been traveling toward us for most of the universe's entire history. We're not seeing it as it exists today, but as it appeared when the cosmos was still young, still forming its current identity. The expansion of space itself adds another layer of complexity to our understanding. By the time light from these distant structures reaches us, the structures themselves may have changed beyond recognition, stretched and evolved by billions of years of cosmic expansion. We're looking at fossils of immensity, preserved in light. The formation of the cosmic web tells a story that began with the Big Bang itself. In those first moments, matter wasn't distributed perfectly evenly throughout space. Tiny fluctuations in density, quantum ripples stretched by cosmic inflation, became the seeds of everything we see today. Over billions of years, gravity amplified these small differences, pulling matter into increasingly dense regions. Dark matter played a crucial role in this cosmic construction project. Though invisible to our telescopes, this mysterious substance creates gravitational scaffolding that guides the formation of galaxies and larger structures. Computer simulations that account for dark matter's influence recreate the cosmic web with remarkable accuracy, showing us that what we observe isn't accidental but inevitable. The web emerges naturally from simple physical laws acting over cosmic timescales, gravity, expansion, and those primordial quantum fluctuations combine to weave the largest tapestry in existence. There's something beautiful about this inevitability, the way complexity arises from simplicity when given enough space and time to unfold. What makes the cosmic web truly remarkable is how it gives texture to the universe. Instead of uniform emptiness, we find intricate patterns of density and void, light and darkness. If we could somehow step outside our observable universe and look back, we'd see a delicate lacework of glowing filaments against the cosmic dark. Galaxies would appear as mere decorations on these vast threads, details in a much grander design. The voids deserve equal attention to the filaments. These enormous empty regions, sometimes 300 million light-years across, contain almost nothing. They're bubbles of near-perfect emptiness in an otherwise structured universe. To find yourself drifting through such a void would mean leaving behind the familiar glow of galaxies, entering a darkness punctuated only by the occasional faint glimmer of distant light. These empty spaces make up most of the universe's volume. The matter we can see, all those galaxies and stars that seem so impressive, actually occupies a tiny fraction of cosmic space. Most of reality consists of these vast, dark, nearly empty regions. There's something humbling about realizing that absence, not presence, dominates the universe's architecture. The patterns we observe in the cosmic web often appear designed, almost intentional. The branching filaments, the clustering nodes, the elegant symmetries all suggest some guiding intelligence, but this apparent design emerges naturally from physical laws. No architect required. Simple rules given enough time and space create complexity that rivals any conscious creation. Our view of the cosmic web faces fundamental limitations. We can only observe the portion of the universe from which light has had time to reach us since the Big Bang. Beyond this horizon, more filaments and voids almost certainly exist, but they remain forever hidden as space expansion carries them away faster than light can travel toward us. This observational boundary means that the largest structure we can describe is limited not by what exists, but by what we can detect. The true extent of cosmic architecture remains unknown, possibly unknowable. Reality extends beyond our ability to measure it, a reminder that our perspective, however sophisticated, remains finite. From Earth, we can only observe tiny portions of the cosmic web at any given time. A telescope's field of view captures scattered galaxies, individual points of light that must be painstakingly assembled into larger maps over decades of observation. Even our most comprehensive surveys provide only reconstructions, models that attempt to represent scales too vast for direct comprehensive. The cognitive challenge of the cosmic web matches its physical immensity. Human minds evolved to navigate environments measured in miles, not billions of light years. We push our imagination to its limits, trying to grasp these scales, stretching our conceptual frameworks until they threaten to break under the weight of such vastness. Perhaps most humbling of all is the realization that everything we can observe, every galaxy, every cluster, every magnificent filament, represents only part of one cosmic web. The universe may extend infinitely beyond our observable horizon, containing other webs, other structures we'll never detect. Alternatively, what we can see might represent the totality of existence, making our observable web the complete architecture of reality. Either possibility challenges our sense of scale and significance. If infinite structures exist beyond our view, our cosmic web becomes just one example among countless others. If our observable universe contains everything that exists, we're witnessing the complete organizational structure of reality itself, the final and ultimate pattern. Standing at this level of cosmic architecture, we see how each previous scale of understanding has been dwarfed by the next revelation. Mountains seemed vast until we discovered oceans. Planets appeared enormous until we found stars. Solar systems looked impressive until we mapped galaxies. Galaxy clusters amazed us until we uncovered the web that connects them all. Now, at the scale of the cosmic web, we confront what may be the largest identifiable structure in existence. Threads of matter and energy stretched across billions of light years, the ultimate expression of cosmic organization. Yet even here, at this pinnacle of observable scale, questions remain about what lies beyond our horizon. The cosmic web represents both an ending and a beginning in our journey of cosmic understanding. It may be the largest structure we'll ever identify, the final rung on the ladder of scale. Or it might be merely another step toward even grander revelations waiting beyond the limits of our current observation. In either case, the web stands as a monument to the universe's capacity for creating order from chaos, structure from simplicity, beauty from basic physical laws. It reminds us that reality operates on scales that dwarf human experience, yet follows principles we can understand and appreciate. The largest thing in the universe emerges from the same fundamental forces that shape our daily lives, a connection that spans the entirety of known existence. The universe has this fascinating way of revealing its grandest secrets through absence rather than presence. Between the bright filaments of galaxies, between the glowing threads where stars gather and shine, there exist regions so empty they challenge our understanding of space itself. These cosmic voids stretch across hundreds of millions of light years, containing almost nothing at all. Think of them as the universe's own meditation chambers, places where silence takes on physical form. The density here drops so dramatically that you might find only a handful of galaxies where thousands should exist. Botus Void stands as one of these magnificent emptinesses, spanning roughly 330 million light-years across. If you placed our entire Milky Way at its center, you could travel for hundreds of millions of years at light speed without encountering another major galaxy. The locals call it the Great Nothing, and that name captures something profound about how emptiness itself can become a presence. What strikes me as remarkable is how these voids aren't mistakes or flaws in cosmic architecture. They're essential features, carved out naturally as gravity pulls matter into denser regions. Material flows toward filaments and clusters, leaving behind these underdense territories. Without voids, the cosmic web simply couldn't exist. Imagine drifting through one of these empty regions. On Earth, we never experience true emptiness. Deserts have sand, oceans have water, even our atmosphere surrounds us constantly. But inside a cosmic void, that emptiness extends beyond human comprehension. Any civilization unlucky enough to evolve, they might look up at their night sky and see almost nothing, concluding they live in a sparse, lonely universe. The scale becomes even more mind-bending when you consider that some voids reach 500 million light-years across. Our own galaxy might actually sit near the edge of something called the KBC void. potentially 2 billion light-years in diameter. If that's true, our entire perspective on cosmic density has been shaped by living on the frontier of nothingness. These empty regions aren't static either. They expand faster than areas filled with matter, gradually pushing filaments farther apart over billions of years. Emptiness turns out to be surprisingly dynamic, actively reshaping the universe's future structure. The largest rooms in existence are growing larger. There's something philosophically unsettling about such vast nothingness. Human minds naturally gravitate toward things we can see and touch, stars and planets, and tangible objects. Emptiness resists our imagination because there's nothing there to picture. Yet these voids occupy more volume than all the visible structures combined. From our vantage point on Earth, we can't directly observe these empty regions. We map them by inference, charting the spaces between galaxies, measuring silence with tools made for light. Scientists essentially draw the shape of nothingness, using absence as their primary data. The philosophical weight of this discovery shouldn't be understated. We're forced to accept that nothingness itself can possess immensity, that the universe's grandest features might be defined by what isn't there rather than what is. The cosmic web emerges from this interplay between presence and absence, fullness and void, like a vast sculpture, where the negative space matters just as much as the material. Different voids have different personalities, if you can call emptiness personal. Some contain a few scattered dwarf galaxies, like distant lighthouses in an ocean of darkness. Others achieve near-perfect emptiness across their entire volume. Each one represents a different experiment in cosmic architecture. The temperature inside these regions tells its own story. With so little matter around to absorb and emit radiation, voids remain significantly cooler than their surroundings. They're not just empty of galaxies, they're empty of energy, creating vast refrigerated chambers floating through space. What fascinates astronomers is how voids seem to repel matter rather than attract it. Unlike the familiar gravitational pull that draws objects together, these regions create what researchers describe as gravitational push, accelerating galaxies away from their boundaries. Emptiness, it turns out, has its own kind of influence. The largest known void, called the giant void, stretches across roughly 1.5 billion light-years. To put that in perspective, if you could somehow shrink it down so that Earth became the size of a marble, the void would still span several city blocks. The mathematics of such emptiness strain our ability to comprehend scale. These discoveries reshape how we think about cosmic real estate. Most of the universe's volume consists of nothing much at all, with all the galaxies, stars and planets we care about squeezed into the remaining fraction. We're essentially living in the cosmic equivalent of a thin film stretched across an enormous bubble. The evolutionary implications are staggering too. Civilizations developing inside major voids might never discover that galaxies exist elsewhere. Their entire cosmology would be based on near emptiness, making them perhaps the loneliest beings in existence. They'd have no way to know that just beyond their observable horizon, the universe teems with structure and activity. As we peer deeper into space and further back in time, these voids help us understand how the universe organized itself after the Big Bang. They're fossil records of cosmic evolution, preserving evidence of how matter clumped and separated over billions of years. Each empty region tells part of the story about how everything else came to be. The ultimate boundary lies beyond even the largest voids, at the edge of the observable universe itself, roughly 46 billion light-years away, in all directions. This represents the horizon beyond which light simply hasn't had enough time to reach us since the beginning of everything. Even emptiness eventually gives way to something even more profound, the limit of knowledge itself. Looking up at the night sky, we're actually seeing the boundary of everything we can ever hope to know. The observable universe represents the absolute limit of human knowledge, not because there's some cosmic wall out there, but because of something far more subtle. Time itself creates our prison. Picture this. Space has been expanding for nearly 14 billion years, and during all that time, light has been racing toward us, from the most distant regions. But here's where it gets really strange. The universe we can actually observe spans about 93 billion light-years across. Wait, that doesn't make sense at first, does it? If the universe is only 13.8 billion years old, shouldn't we only see 13.8 billion light-years in any direction? The answer reveals something profound about reality itself. Space doesn't just sit there, it grows, it stretches, carrying galaxies away from us like dots on an expanding balloon. So when light started its journey, billions of years ago, those distant galaxies were much closer. During the light's long trip to reach us, space kept expanding, pushing those galaxies farther and farther away. By now, they're sitting roughly 46.5 billion light-years away in every direction. This creates a kind of cosmic horizon, a sphere around us that contains everything we can possibly see. It's not that there's nothing beyond this boundary, there almost certainly is, but that information can never reach us, because space itself is expanding faster than light can travel. Within our observable bubble, astronomers estimate there are roughly 2 trillion galaxies. Each galaxy contains billions of stars, each star potentially hosting planets. Some of those planets might harbor life. When you start multiplying those numbers, something strange happens to your mind. It just stops working properly. 2 trillion galaxies, that's 2,000 billion separate island universes, each one a city of suns. Think about what this means for a moment. Even if life is incredibly rare, even if only one planet in a billion develops living creatures, the sheer scale suggests we're swimming in an ocean of possibilities. The universe isn't just big, it's abundant beyond any reasonable comprehension. But there's another twist to this story that makes it even more mysterious. When we look out into space, we're actually looking backward through time. Light takes time to travel, so distant galaxies appear to us as they were billions of years ago, not as they are right now. The most distant galaxies we can detect show us what the universe looked like when it was just a cosmic infant, less than 1 billion years old. This means our observable universe is also a time machine, a record of cosmic history, written in starlight. We can literally see the universe growing up, watch galaxies forming, stars being born, the whole magnificent story unfolding in reverse as we peer deeper into space. At the very edge of what we can observe lies something remarkable, the cosmic microwave background radiation. This is the afterglow of the Big Bang itself. Light that's been traveling toward us for over 13 billion years. About 380,000 years after the universe began, things finally cooled down enough for atoms to form and for light to travel freely for the first time. That ancient light has been stretched by billions of years of cosmic expansion, turning it into microwaves that fill the entire sky. It's the oldest light in existence, a faint whisper from when the universe was less than 500,000 years old. Before that moment, the cosmos was opaque, a hot soup of particles that trapped light completely. So the cosmic microwave background represents the ultimate wall, the furthest back in time we can ever see. Beyond it lies a realm hidden not by distance, but by the fundamental physics of the early universe itself. These numbers, these scales, they do something strange to human language. Words like billion and trillion start to lose all meaning, becoming just sounds we make with our mouths. What matters isn't the precision of these measurements, but the feeling they create, the recognition that we exist inside something larger than thought itself. Try this mental exercise. Imagine shrinking our solar system until the distance from Earth to the Sun becomes just 1 millimeter. On that scale, our entire Milky Way galaxy would be about 100 meters across, roughly the length of a football field. Our local group of galaxies would span about 1 kilometer. But the observable universe, even on this incredibly compressed scale, would still wrap around the Earth many times over, stretching tens of thousands of kilometers. That's one way to bring these cosmic distances down to something our minds can almost grasp. Though even then, understanding slips away like water through your fingers. Here's something that might surprise you. We're sitting at the center of the observable universe, but that doesn't make us special at all. Every single point in the cosmos sits at the center of its own observable sphere. A galaxy 10 billion light-years away would see itself surrounded by its own cosmic horizon, its own collection of distant galaxies, fading into ancient light. The universe doesn't have a center, but every observer creates their own personal boundary of knowledge. We're not cosmically important, we're just here, looking out at our own particular view of infinity. This horizon shapes everything we can know about reality. Because we can't see beyond it, we have no idea whether the universe repeats itself, whether it goes on forever, whether our little bubble of visibility is typical or completely unique. The largest thing we can describe is also the most mysterious thing we can imagine, and when you really think about our place in all this, the perspective becomes almost overwhelming. We're sitting on a small, rocky planet, orbiting an ordinary star, in the outer regions of a typical galaxy, within a local group, inside a supercluster, surrounded by cosmic web, all contained within the observable universe. Each layer dwarfs everything inside it, until finally we reach that ultimate boundary where all of human knowledge ends. But even this cosmic horizon might not be the final word on immensity. Within our observable universe, astronomers keep discovering structures that push against the very limits of what seems possible. Walls of galaxies stretching across billions of light years, alignments so vast they challenge our theories about how the universe should work, and beyond our horizon, hidden forever from our view, something even larger might be waiting. Structures so immense that our entire observable universe might be just a tiny fragment of something unimaginably greater. The cosmos presents us with a peculiar paradox. We spend our lives measuring, cataloging, mapping every corner of our observable universe. Yet, the more precisely we chart this cosmic territory, the more acutely we realize how little we actually see. Our observable universe stretches nearly 93 billion light-years across. That sphere contains hundreds of billions of galaxies, each one a sprawling city of billions of stars. But this immense catalogue, this cosmic census we've worked so hard to complete, represents only our horizon, not the edge of everything that exists. Think about standing on the deck of a ship in the middle of an ocean. You see water extending to a perfect circle around you. That circle feels like a boundary, like the edge of the world itself. But of course, it's just the limit of your vision. Sail in any direction, and new horizons appear endlessly. The cosmic horizon works similarly. Beyond what we can observe, space almost certainly continues. The question isn't whether more universe exists out there. The question is, how much more, and what strange forms it might take. The simplest possibility is also the most mind-bending. The universe might simply go on forever, infinitely, in all directions. No walls, no boundaries, no outside. Just more galaxies, more stars, more planets, extending without end. Infinity is a concept that makes our brains stumble. We're built to think in terms of edges, limits, containers. But infinity offers none of these familiar landmarks. If space truly extends forever, mathematics tells us something remarkable must happen. Within an infinite expanse, every possible arrangement of matter has to occur somewhere. That means there would be galaxies identical to our Milky Way scattered throughout the cosmos. Solar systems exactly like ours, planets precisely matching Earth, down to every mountain range and ocean. Even copies of you sitting wherever you are right now, contemplating these same thoughts. Not through some mystical process, but simply because infinity demands repetition. In endless space, patterns eventually recur. This isn't science fiction speculation. It's a logical consequence of infinite space combined with finite ways that matter can arrange itself. The number of possible configurations is vast, but not unlimited. Given infinite space to work with, those configurations must repeat. The immensity here isn't just about distance. It's about the strange implications of endlessness itself. But infinity isn't the only possibility. The universe might be finite, yet still have no edges. Picture the surface of a sphere, like Earth. You can walk in any direction without ever hitting a boundary, yet the total surface area remains limited. If you keep walking in a straight line long enough, you'll eventually return to your starting point. The cosmic equivalent would be a universe that curves back on itself. Travel far enough in one direction, and you might theoretically return to where you began, though the distances involved would make such a journey impossible, even across cosmic timescales. This creates a different kind of immensity. Not infinite space, but endless journeying within finite bounds. A universe without edges that still contains itself, like a cosmic riddle written in the language of geometry. Some theories push these ideas even further. Our entire observable universe might be just one bubble floating in a vast multiverse. Imagine cosmic foam, where each bubble represents a complete universe with its own physical laws, its own constants, its own possibilities for complexity and life. These universe bubbles might drift independently through some higher dimensional space. Occasionally, they might even collide, potentially leaving subtle imprints we could detect in the cosmic microwave background radiation. If such a multiverse exists, then asking about the largest thing becomes layered. The largest thing in our universe might be some massive galaxy cluster or cosmic web structure, but the largest thing in the multiverses could be the multiverses itself, an infinite sea of universes beyond universes. Immensity becomes hierarchical, stacked like cosmic nested dolls. Higher dimensions add another layer of strangeness. Just as a flat piece of paper exists within three-dimensional space, our three-dimensional universe might be embedded within some higher dimensional reality. We'd be like creatures living on the surface of that paper, unaware of the vast space extending above and below us. What we perceive as the immense cosmos might be merely a thin slice of something far grander, a shadow cast by structures we can't directly sense. Even within our observable universe, we keep discovering structures that challenge our understanding of cosmic scale. Some alignments of galaxies stretch so far across space that they seem to violate the principle that the universe should look smooth and uniform on the largest scales. These cosmic walls and filaments hint that our current picture of immensity might be incomplete. Perhaps the universe is more connected, more patterned, more organized than our theories predict. Time adds its own dimension to these questions about ultimate size. We observed the universe as it existed 13.8 billion years ago at the most distant edges of our vision. But what came before that beginning? Some theories suggest the universe cycles endlessly, expanding and contracting in eternal rhythm. Others propose that time itself began with the Big Bang, making questions about before meaningless. Either way, immensity extends not just through space, but through time, reaching backward and forward in ways that stretch our ability to conceptualize. The expansion of space itself creates another puzzle. As the universe grows, distant galaxies get carried away from us faster than light can travel. They slip beyond our cosmic horizon, still existing but forever invisible to us. If expansion continues indefinitely, more and more of the cosmos will fade from view. Future observers might see only their local group of galaxies, isolated in an ocean of darkness. The immensity will still be there, but hidden. Our window into the larger cosmos will gradually close. These aren't just abstract scientific puzzles, they reflect something fundamental about human nature. We're creatures who look toward horizons and wonder what lies beyond them. Ancient sailors stared at endless oceans. Early explorers studied maps, always asking what existed past the edges. The cosmos presents the same mystery, scaled up to the ultimate level. Each possibility for what lies beyond our observable universe expands our sense of scale differently. An infinite universe makes us confront endlessness and repetition. A finite but unbounded cosmos challenges us with spaces that curve back on themselves. A multiverse suggests hierarchies of reality beyond our direct experience. Higher dimensions hint at forms of existence we can barely imagine. Each option redefines what we mean when we talk about immensity. Perhaps the largest thing in the universe isn't located within the universe at all. Perhaps it is the universe itself, or whatever vast structure contains our universe. We've climbed a ladder of scale, from mountains to planets, to stars, to galaxies, to clusters, to superclusters. Now, At the edge of the observable cosmos, we face not a final answer, but a collection of possibilities, each one more immense than anything we can directly measure or prove. The scale of our speculation has itself become a kind of immensity, larger than measurement, larger than certainty, as vast as our capacity to wonder about what might exist beyond the edges of everything we've ever seen. Looking up at the night sky, we encounter something remarkable about ourselves as thinking beings. We can grasp distances that stretch billions of light years, even though our brains weigh just over a kilogram. This fragile network of neurons, evolved for walking across plains and climbing trees, somehow manages to map entire galaxies and ponder infinity itself. The journey outward through scales reveals layer after layer of structure. Mountains give way to planets, planets to star systems to galaxies. Each step redefines what we thought was large. The sun, which feels overwhelming in its power, appears modest beside a red supergiant. Our Milky Way, containing hundreds of billions of stars, becomes just one galaxy among countless others. But here's where things get interesting. The observable universe, immense beyond description, might itself be only a fragment of something even larger. Scientists talk about cosmic webs, vast filaments of matter stretching across unimaginable distances. Between these structures lie voids, regions so empty they challenge our understanding of nothingness itself. When we contemplate these scales, it's natural to feel small, even insignificant. Earth holds every human story, every life, every memory, yet it's smaller than a grain of dust compared to a galaxy. If size alone determined meaning, our existence would seem trivial, erased by sheer immensity. Yet meaning doesn't work that way. Significance isn't measured in light years, but in awareness, in the capacity to wonder. The fact that we can contemplate these scales at all reveals something extraordinary about consciousness. We are small in body but vast in thought, tiny creatures capable of reaching across the cosmos through curiosity alone. There's also comfort in recognizing our connection to this vastness. We aren't separate from cosmic immensity. We're made of it. The atoms in our bodies were forged inside stars, scattered by supernovas, then gathered into planets. Every breath of oxygen, every trace of iron in our blood, every bit of calcium in our bones was once part of ancient stellar furnaces. The universe doesn't diminish us, it situates us, like drops belonging to an ocean. We belong to this cosmos. When we look up at night, most of what we see is history. Light has traveled for years, centuries, even millennia before reaching our eyes. Every star sends us a message from the past, every galaxy a postcard from billions of years ago. This means we live surrounded not just by distances but by ages. Our brief moment connects to a chain of moments stretching back nearly 14 billion years to the universe's beginning. It's humbling, but also grounding. We're part of an unfolding story that began long before us and will continue long after. Interestingly, vastness and intimacy aren't opposites. You can stand at an ocean's edge, feeling both the immensity of water stretching to the horizon and the intimacy of sand between your toes. The cosmos works similarly. You can think about galaxies spanning hundreds of thousands of light years while feeling sunlight warm on your skin. You can imagine galaxy clusters colliding while noticing a candle's flicker in a quiet room. Holding vastness in a human heart doesn't mean abandoning the small. It means seeing both scales simultaneously, the grand and the close, the infinite and the immediate, woven together like threads in an incomprehensibly large tapestry. There's quiet reassurance, knowing the universe doesn't require our understanding to continue. Stars burn, galaxies rotate, clusters evolve, cosmic webs stretch, all without our permission or awareness. This frees us to engage not as masters but as participants, to wonder without needing control, to admire without needing ownership. The layered nature of reality becomes apparent when you consider all scales together. Each level builds on the one before it, each perspective reshaping the meaning of the last. No single scale cancels another. The small remains meaningful within the large, the personal stays real within the cosmic. Immensity can inspire awe, but awe isn't the same as fear. Awe is the widening of perspective, the expansion of what we thought possible. It's recognition that there's always more than we can see or know. This awareness can be surprisingly calming, putting daily worries into perspective against the backdrop of billions of light years. But vastness exists in both directions. While the universe stretches outward to cosmic horizons, it also reaches inward to subatomic scales. Both are immense in their own way, both beyond everyday senses, both requiring imagination to grasp. We exist in the middle, bridging the small and the large, and perhaps that's the most human response to immensity. The largest thing in the universe depends on where you stop climbing the ladder of scale. A mountain, planet, star, galaxy, cluster, supercluster, filament, or horizon. Each seems largest until you step outward again. Beyond each step lies another, and the truest answer might be that the largest thing is always the next thing, always what lies just beyond our current sight. Wonder remains our way of accessing this vastness, not through numbers but through presence. It's available in any night sky, in photographs of distant galaxies, in the thought of light beams traveling billions of years to meet our eyes right now. And holding that thought, that there's always more, may be the best way to carry cosmic vastness in a human heart. The universe stretches out in ways that make our minds feel dizzy when we really think about it. Every single thing we can touch, every object in our daily lives, sits somewhere on this incredible ladder of size that goes from the tiniest particles all the way up to galaxy clusters that span billions of light years. It's like we're living right in the middle of this cosmic hierarchy, with smaller worlds below us and impossibly vast realms above us. When we hold something simple in our hands, like a coin or a stone, we're actually holding billions upon billions of atoms. Each of those atoms contains a nucleus surrounded by electrons, and inside that nucleus are protons and neutrons made of even smaller things called quarks. The empty space between these particles is enormous compared to their actual size. If an atom were the size of a football stadium, the nucleus would be like a marble sitting in the center. But then we zoom out from our human scale, and suddenly, we become the small things. Our planet Earth, which feels so solid and permanent under our feet, is really just a tiny speck orbiting an ordinary star. The sun itself, massive as it seems to us, is just one of hundreds of billions of stars in our galaxy. And our galaxy, the Milky Way, is just one of trillions of galaxies scattered throughout the observable universe. The distances between these cosmic objects are so large that light, the fastest thing we know, takes years and years to travel between them. The light from the nearest star takes over 4 years to reach us. The light from distant galaxies has been traveling for billions of years, showing us what those places looked like when the universe was much younger. There's something both humbling and comforting about realizing our place in this vast hierarchy. We exist at a very special scale, right where chemistry and biology can work their magic to create complex, thinking beings. We're big enough that quantum uncertainty doesn't make our daily lives unpredictable, but small enough that we don't collapse under our own gravity, like stars do. The materials in our bodies were forged inside ancient stars that lived and died billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it came from nuclear reactions deep inside stellar cores. When those massive stars reached the end of their lives, they exploded and scattered these elements into space, where they eventually became part of new stars, planets, and eventually, us. This cosmic recycling has been going on for most of the universe's history. The hydrogen and helium that make up most of ordinary matter were created in the first few minutes after the Big Bang. Everything else, all the heavier elements that make planets and life possible, had to be built up slowly over billions of years inside successive generations of stars. The structures we see in the universe today, from solar systems to galaxy clusters, formed gradually as gravity pulled matter together. What started as tiny ripples in the density of the early universe grew over cosmic time into the web-like pattern of filaments and voids that we observe today. Dark matter, which we can't see directly, but can detect through its gravitational effects. played a crucial role in building these large-scale structures. Even our understanding of size itself has evolved over human history. Ancient peoples could only imagine the scale of their immediate surroundings. The invention of telescopes revealed that stars were distant suns, that nebulae were actually other galaxies, that the universe was far larger and older than anyone had imagined. Each new generation of instruments has pushed back the boundaries of the known, revealing new realms of existence at both larger and smaller scales. The concept of infinity lurks at both ends of this scale. We don't know if space goes on forever, or if matter can be divided infinitely. These questions touch on some of the deepest mysteries in physics and philosophy. What we do know is that the observable universe has a finite size, simply because light has only had a finite time to travel since the Big Bang occurred about 14 billion years ago. Within this observable realm, the patterns and structures we see tell a story of cosmic evolution, of simple beginnings giving rise to incredible complexity. The same physical laws that govern the motion of planets also determine how atoms bond together and how galaxies collide and merge. There's a beautiful unity underlying all the diversity we observe, from the smallest scales to the largest.